A gas bridge is defined by its dynamical and thermodynamic behavior within an interacting galactic system. It is a coherent, elongated structure of diffuse gas that physically and kinematically connects two galaxies, sharing a continuous velocity field that links their orbital motion. This dynamical continuity is the defining criterion. The gas occupies intermediate velocities between the parent systems, tracing a real physical connection rather than a chance alignment along the line of sight. The bridge exists because gravitational and hydrodynamic forces act on gaseous components during an interaction in a way that preserves continuity between the galaxies for a limited time. This definition distinguishes gas bridges from other large-scale gaseous structures. Tidal tails arise when gravitational torques during a close encounter extract angular momentum from a galaxy, launching material outward into intergalactic space. These features are usually one-sided, often rich in stars, and their kinematics reflect ejection rather than connection. Stellar streams represent a different regime, forming through the gradual stripping of stars and gas from a satellite galaxy as it orbits a more massive host. Streams are dynamically cold, long-lived, and trace stable orbital paths over billions of years. Cosmic filaments belong to an entirely separate category. They are primordial structures shaped by dark matter on megaparsec scales, established early in cosmic history and guiding the formation of galaxies themselves. Gas bridges operate on smaller scales set by galactic halos and arise directly from galaxy-galaxy interactions, making them secondary, transient structures rather than fundamental components of the cosmic web. In physical extent, gas bridges are large relative to galaxies, yet delicate in structure. Typical lengths range from several tens of kiloparsecs to several hundred kiloparsecs, corresponding to distances of hundreds of thousands of light years. A bridge can therefore span a region comparable to, or exceeding, the diameter of a spiral galaxy's stellar disk. Despite this length, gas bridges remain narrow. Their widths are often limited to a few kiloparsecs, with even smaller vertical thicknesses. This extreme geometry reflects the physical processes that create them. Tidal forces stretch gas along the direction of interaction, while pressure support and external heating prevent collapse perpendicular to the bridge axis, producing long, thin structures with low surface density. The dominant constituent of gas bridges is neutral atomic hydrogen, commonly referred to as HI. This phase accounts for most of the directly observable mass in many bridges and is detected through its 21 cm hyperfine transition. At the low densities typical of bridges, atomic hydrogen emits essentially no visible light, which explains why these structures remained undetected in optical surveys for much of the 20th century. The neutral gas often shows internal substructure, appearing clumpy or filamentary within radio maps, reflecting variations in density and the history of tidal stripping during the interaction. A substantial fraction of bridge material exists in a warm ionized phase. This gas is maintained in an ionized state by ultraviolet radiation originating from several sources, including star-forming regions in the parent galaxies, evolved stellar populations, shocks generated during the interaction, and the diffuse extragalactic ultraviolet background. Because the density of this ionized gas is extremely low, it rarely produces detectable emission. Instead, it is most effectively revealed through absorption line spectroscopy against background quasars or galaxies. In many systems, the ionized component contains a mass comparable to or greater than the neutral component, indicating that radio observations alone capture only part of the total baryonic content of a bridge. Molecular gas represents the rarest phase within gas bridges. When present, it is usually inferred from molecules such as carbon monoxide, which serve as tracers for molecular hydrogen. Molecular gas requires efficient cooling and shielding from ultraviolet radiation, conditions that are difficult to achieve in the exposed, low-density environments of bridges. As a result, molecular material is confined to small, localized regions where compression or shock interactions temporarily raise density and allow cooling. These regions are transient and do not dominate the mass, dynamics, or long-term evolution of the bridge. The characteristic densities of gas bridges are extremely low compared to those found in galactic disks. In spiral galaxies, interstellar gas commonly reaches densities of order 1 particle per cubic centimetre or higher, with molecular clouds exceeding this by several orders of magnitude. In contrast, gas bridges typically exhibit densities of 1/10,000th of a particle per cubic centimetre, 1/10,000th, or even lower. At such densities, particle collisions are infrequent, radiative cooling is inefficient, and the gas behaves as a diffuse plasma governed primarily by large-scale gravitational and hydrodynamic forces rather than local cloud physics. Temperature follows directly from this diffuse state. Neutral regions within gas bridges commonly reside near 10,000 Kelvin, a temperature set by the balance between photoionization heating and atomic cooling processes. Ionized regions often reach significantly higher temperatures, ranging from several 100,000 Kelvin to more than 1,000,000 Kelvin. These elevated temperatures arise from shock heating during the formation of the bridge and from interactions with the hot circumgalactic halos surrounding massive galaxies. Once heated, the gas cools slowly, with cooling times often comparable to or longer than the lifetime of the bridge itself. These thermodynamic conditions strongly suppress star formation. Star formation requires gas to cool efficiently, fragment into dense clumps, and reach a state where self-gravity overcomes thermal pressure and turbulence. In gas bridges, the combination of low density, high temperature, and continuous external heating prevents this sequence from occurring on large scales. Even when small overdensities develop, tidal shear stretches them apart, and thermal pressure counteracts further collapse. As a result, stars are typically absent, and when star formation does occur, it is confined to small localized pockets that contribute negligibly to the total mass and luminosity of the bridge. The gravitational properties of gas bridges further limit their stability. The total mass of a bridge is modest relative to its enormous size, and it is distributed over a volume far larger than that of a galactic disk. Unlike galaxies, gas bridges lack a substantial dark matter component. They are composed almost entirely of baryonic gas stripped from galactic disks or halos, without the deep gravitational potential well required for long-term confinement. Internal gravity is therefore weak compared to thermal pressure, turbulence, and external forces. The evolution of a gas bridge is governed by a balance between stretching, heating, and dispersal. Gravitational forces from the parent galaxies shape and elongate the structure, while interactions with hot halo gas ionize and erode it. Over hundreds of millions of years, densities decrease further, ionization increases, and the bridge gradually dissolves. Portions of the gas may be reaccreted into the circumgalactic halos of the interacting galaxies, while other fractions disperse into the intergalactic medium. This transient nature is a fundamental characteristic of gas bridges. Together, these properties define gas bridges as a distinct astrophysical phenomenon. They are dynamically connected, yet gravitationally fragile, extensive in scale, yet low in mass, and dominated by diffuse gas phases that resist cooling and collapse. Their observational invisibility in optical light follows directly from their physical state, and their temporary existence makes them powerful tracers of ongoing or recent galaxy interactions. Through gas bridges, galaxies are revealed as systems that exchange matter across vast distances, connected by structures that briefly persist before dissolving back into the surrounding cosmic environment. Gas bridges are rendered invisible in optical light by a combination of atomic physics, thermodynamic conditions, and observational limitations that work together to suppress visible emission. Their invisibility is not incidental or due to instrumental shortcomings alone. It is a direct consequence of how diffuse hydrogen behaves in low-density environments and how light is generated, absorbed, and contrasted against the cosmic background. Understanding this invisibility requires shifting perspective away from stars and luminous nebulae and toward the physical requirements for light production in tenuous intergalactic gas. Hydrogen, the dominant constituent of gas bridges, emits visible light only under very specific conditions. In familiar astronomical environments, such as star-forming regions or emission nebulae, hydrogen glows because it is both ionized and sufficiently dense. When ultraviolet photons from nearby stars ionize hydrogen atoms, free electrons later recombine with protons and cascade down energy levels, emitting photons at characteristic wavelengths. One of the most prominent of these is the hydrogen alpha line in the red portion of the visible spectrum. This process depends critically on density. The rate at which recombination events occur scales with the square of the particle density because it requires electrons and protons to encounter each other. In gas bridges, particle densities are so low that recombination events are exceedingly rare. Even if hydrogen is partially ionized, the probability that an electron will recombine within a reasonable timescale is small, and visible emission becomes vanishingly faint. At the densities typical of gas bridges, hydrogen can remain ionized for extraordinarily long periods. Recombination timescales in such environments can reach hundreds of millions of years, comparable to or exceeding the lifetime of the bridge itself. This means that once hydrogen is ionized, it does not readily return to a neutral state that could emit line radiation efficiently. In contrast to dense nebulae, where recombination happens quickly and produces bright optical emission, the gas in bridges remains in a low emissivity state for most of its existence. The result is gas that is physically present but optically silent. Even when hydrogen is predominantly neutral, visible emission remains suppressed. Neutral hydrogen does not emit strongly in the optical under typical intergalactic conditions. Its most important emission mechanism is the hyperfine spin-flip transition that produces radiation at a wavelength of 21 centimeters, well outside the optical range. This transition is extraordinarily weak, but it becomes detectable because enormous volumes of neutral hydrogen contribute collectively. In the optical regime, however, neutral hydrogen lacks efficient emission pathways, unless it is excited by collisions or intense radiation fields, both of which are rare in the diffuse environments of gas bridges. Ionization state plays a central role in determining visibility, but it does so in a subtle way. Gas bridges often exist in a partially ionized state, influenced by ultraviolet radiation from nearby galaxies, hot halo gas, and the diffuse extragalactic ultraviolet background. This radiation field is sufficient to keep hydrogen ionized, but insufficient to generate strong emission. The gas absorbs energy, remains warm, and stays ionized, yet emits very little in return. This imbalance between energy input and radiative output is a defining feature of low-density plasma. The gas stores thermal energy rather than radiating it efficiently, which further suppresses optical detectability. Dust, a critical component of optical visibility in galaxies, is largely absent from gas bridges. In galactic disks, dust grains play two important roles. They absorb ultraviolet and optical light and re-radiate energy in the infrared, and they provide surfaces that facilitate cooling and molecule formation. Dust also enhances optical visibility by scattering and absorbing starlight, creating contrast against the background. Gas bridges lack significant dust content for several reasons. Dust grains are easily destroyed by shocks, heating, and sputtering in hot gas, all of which accompany galaxy interactions. In addition, tidal stripping preferentially removes gas rather than dust-rich molecular clouds, leaving bridges depleted in solid particles. The absence of dust has direct observational consequences. Without dust to scatter or absorb light, gas bridges do not produce extinction features or reddening signatures that could reveal their presence against background galaxies. In optical images, there is no silhouette, no dark lane, and no diffuse glow. The gas simply blends into the background sky. This lack of dust also prevents efficient cooling, reinforcing the high temperatures that suppress recombination and emission. The invisibility of gas bridges is therefore self-reinforcing. Low dust content leads to high temperatures, which lead to low emission, which makes detection difficult. Optical invisibility is compounded by a severe contrast problem. Even if gas bridges emitted some visible light, that emission would be extraordinarily faint compared to the brightness of galaxies, stars, and the diffuse sky background. The surface brightness of a gas bridge in optical wavelengths is many orders of magnitude below the detection limits of traditional surveys. Optical telescopes are optimized to detect compact, high-contrast sources such as stars and galaxies. Extended, low-surface brightness features are inherently difficult to observe, especially when they span large angular scales and lack sharp edges. The night sky itself is not dark in an absolute sense. It contains airglow, scattered starlight, zodiacal light from interplanetary dust, and integrated light from unresolved galaxies. Against this complex and fluctuating background, the extremely weak emission from a gas bridge is effectively invisible. Increasing exposure time does not necessarily solve the problem, because systematic noise and background subtraction errors begin to dominate long before the signal from the bridge emerges. This limitation is fundamental rather than technical, rooted in the physics of light production and detection. These constraints explain why early optical surveys missed gas bridges entirely. Historically, astronomical surveys focused on cataloguing stars, nebulae, and galaxies using photographic plates and later electronic detectors sensitive to visible light. Survey strategies prioritized angular resolution and point source sensitivity rather than surface brightness sensitivity. Even when deep exposures were taken, they were optimized to reveal faint galaxies, not diffuse intergalactic gas. The data reduction techniques of the time often removed large-scale, low-contrast features as a background noise, inadvertently erasing any signature of gas bridges. The conceptual framework of early astronomy also contributed to their absence from catalogues. Space between galaxies was long regarded as empty or nearly so, populated only by occasional stars or faint background galaxies. This assumption influenced both observational priorities and interpretation. When faint, diffuse features were detected, they were often attributed to instrumental artifacts, scattered light, or foreground effects, rather than recognized as genuine astrophysical structures. Without a theoretical expectation for gas bridges, there was little motivation to search for them explicitly. The invisibility of gas bridges in optical light reinforces a broader misconception about intergalactic space. The region between galaxies appears empty because it lacks stars, not because it lacks matter. Gas bridges demonstrate that baryonic material can exist in large quantities while remaining almost entirely undetectable in visible wavelengths. This gas participates actively in galaxy evolution, transporting mass, energy, and chemical elements across vast distances. Its invisibility is therefore a limitation of human perception and instrumentation, not a reflection of physical absence. Modern astronomy has overturned the idea of empty intergalactic space by expanding observational techniques beyond the optical regime. Radio observations of neutral hydrogen, ultraviolet absorption line studies, and X-ray measurements of hot gas have revealed a universe filled with diffuse matter. Gas bridges occupy an intermediate position within this hidden ecosystem. They are denser than the average intergalactic medium, but far more tenuous than galactic disks. Their optical silence places them squarely in the gap between traditional observational categories, explaining why they remained undiscovered for so long. The misleading appearance of emptiness has profound implications for how galaxies are understood. Optical images suggest that galaxies are isolated islands of light separated by voids. Gas bridges reveal a different reality. Galaxies are embedded in extended gaseous environments that overlap, interact, and exchange material. The absence of visible light masks these connections, fostering an incomplete picture of galactic ecosystems. Once observations extend beyond the optical, the space between galaxies emerges as an active, structured medium rather than a passive void. Optical invisibility, then, is not a mystery, but an expected outcome of well-understood physical principles. Low densities suppress recombination and emission. Ionization persists for long timescales. Dust is scarce, and surface brightness falls far below detection thresholds. Early surveys lacked both the sensitivity and the conceptual framework to reveal such structures. Gas bridges challenge intuitive notions of visibility in astronomy, demonstrating that the presence of matter does not guarantee the presence of light. Through them, the universe reveals a hidden architecture that becomes apparent only when observation follows physics rather than appearance. The primary reason gas bridges became observable at all is the existence of a single, extraordinarily weak but uniquely powerful atomic transition, the 21-centimeter line of neutral hydrogen. This radio emission does not merely trace gas, it reveals kinematics, structure, and continuity in environments where optical methods fail entirely. For gas bridges, the 21-centimeter line is not just a detection tool, but the defining observational signature that allows these structures to be identified, mapped, and distinguished from unrelated intergalactic material. The 21-centimeter line arises from a quantum mechanical property of the hydrogen atom. Neutral hydrogen consists of a proton and an electron, each possessing intrinsic angular momentum known as spin. These spins can be aligned in the same direction or in opposite directions. When the spins are parallel, the atom occupies a slightly higher energy state than when they are anti-parallel. The transition from the higher energy parallel configuration to the lower energy anti-parallel configuration produces the emission of a photon with a wavelength of approximately 21 centimeters, corresponding to a frequency of about 1420 megahertz. This process is called the hyperfine spin-flip transition. The transition is extremely improbable for any individual atom. The spontaneous decay rate is so low that a single hydrogen atom in isolation would, on average, take millions of years to emit a single 21-centimeter photon. What makes the line observable is not the strength of the transition, but the sheer abundance of hydrogen in the universe. When enormous volumes of neutral hydrogen are present, as in galactic disks, halos, and gas bridges, the collective emission becomes detectable. This property makes the 21-centimeter line uniquely sensitive to diffuse cold atomic gas that would otherwise remain invisible. In gas bridges, the physical conditions are particularly favorable for the persistence of neutral hydrogen. While ionizing radiation permeates intergalactic space, much of the gas in bridges exists at temperatures around 10,000 Kelvin, where hydrogen can remain neutral if the ionizing flux is modest and densities are low. At these densities, recombination and ionization processes reach a balance that allows a significant fraction of hydrogen atoms to remain neutral over long timescales. This neutral fraction is sufficient to dominate the observable mass of the bridge in radio surveys. Neutral hydrogen dominates the detectable mass of gas bridges not because it is necessarily the most abundant phase overall, but because it is the phase most efficiently traced. Ionized gas, which may equal or exceed the neutral component in total mass, produces little emission at radio frequencies and is instead detected through absorption or X-ray emission under specific conditions. Molecular gas, by contrast, is rare in bridges due to the difficulty of cooling and shielding. As a result, high becomes the primary observational proxy for the existence, extent, and structure of the bridge, even when it does not represent the full baryonic budget. Radio telescopes detect the 21-centimeter line by measuring extremely faint signals spread over large areas of sky. Sensitivity is therefore a critical limitation. The detectability of a gas bridge depends on the collecting area of the telescope, the system temperature, the integration time, and the angular resolution. Single-dish radio telescopes excel at detecting large-scale, low-surface brightness emission, but lack fine spatial resolution. Interferometric arrays provide higher resolution, but can miss extended emission if their shortest baselines are insufficiently small. As a result, the most successful observations of gas bridges often combine data from multiple instruments to capture both large-scale structure and fine detail. Sensitivity limits translate directly into column density thresholds. Column density measures the number of hydrogen atoms integrated along the line of sight and is the relevant quantity for 21 centimeter detection. For most modern radio surveys, the practical detection limit lies around column densities of roughly 10 to the 19th atoms per square centimetre, although this varies depending on observing strategy and instrumentation. Gas bridges often sit near or below this threshold, meaning that only the densest portions are readily detectable. Large fractions of bridge material may remain undetected, even in deep surveys, reinforcing the idea that observed bridges represent lower limits on total gas content. The diffuse nature of gas bridges also means that their emission is spread over many velocity channels. The 21 centimeter line is Doppler shifted by the motion of the gas along the line of sight, allowing astronomers to construct three-dimensional data cubes with two spatial dimensions and one velocity dimension. These velocity maps are essential for identifying gas bridges. A genuine bridge exhibits a continuous velocity gradient connecting the systemic velocities of the two galaxies it links. Rather than appearing as isolated clumps at unrelated velocities, the gas forms a smooth kinematic structure that traces the dynamical interaction. Velocity coherence is the strongest evidence that a detected structure is a true gas bridge. In position velocity space, bridges appear as elongated features that span a range of velocities in an ordered fashion. This coherence distinguishes them from random intergalactic gas clouds or foreground material. Chance line-of-sight gas may overlap spatially with galaxies, but it lacks the systematic velocity connection that characterizes a bridge. By analyzing velocity fields, astronomers can demonstrate that the gas is dynamically associated with both galaxies and participates in their interaction. Distinguishing gas bridges from unrelated line-of-sight gas requires careful analysis. Intergalactic space contains diffuse hydrogen associated with the cosmic web, satellite debris, and extended halos. These components can produce 21 centimeter emission at similar velocities, creating ambiguity. The resolution lies in combining spatial continuity, velocity coherence, and contextual information about galaxy interactions. A gas bridge aligns geometrically with the interacting galaxies, spans the region between them, and exhibits velocities that interpolate smoothly between their rotation curves or systemic motions. Random gas clouds lack this combination of properties. Column density gradients also provide diagnostic power. In a gas bridge, column density often decreases smoothly away from the parent galaxies, reflecting tidal stripping and subsequent dilution. This gradient contrasts with isolated clouds, which tend to have more symmetric or compact distributions. Additionally, bridges often show asymmetric density enhancements corresponding to regions of compression or interaction with halo gas, features that further support an interaction-driven origin. The ability of the 21 centimeter line to reveal velocity information transforms gas bridges from faint smudges into dynamic structures. Unlike optical images, which provide only projected positions, radio observations expose the motion of gas and its relationship to galactic dynamics. This kinematic information allows astronomers to reconstruct interaction histories, estimate mass transfer rates, and constrain the gravitational potentials of the galaxies involved. Gas bridges thus serve as tracers of both matter distribution and dynamical evolution. The reliance on radio detection explains why gas bridges were unknown before the development of sensitive 21 centimeter surveys. early radio astronomy lacked the sensitivity and resolution required to detect such diffuse structures. As instrumentation improved, surveys began to reveal extended high envelopes around galaxies, followed by faint connections between interacting systems. Many gas bridges were discovered unintentionally, emerging only after data were processed to emphasize low surface brightness emission rather than compact sources. Despite these advances, current observations still capture only part of the picture. Sensitivity limits mean that detected bridges likely represent the densest regions of much larger, more diffuse structures. The true extent of neutral hydrogen connections between galaxies may be significantly greater than what is currently observed. Future radio facilities with increased sensitivity and improved coverage of short baselines are expected to reveal bridges with lower column densities, extending the known population and filling in gaps between detected features. The 21 centimetre hydrogen line therefore occupies a central role in the study of gas bridges. Its quantum mechanical origin allows neutral hydrogen to radiate in environments where no other emission mechanism is effective. Its sensitivity to velocity enables the identification of coherent structures and the rejection of chance alignments. Its limitations define what can and cannot be observed, shaping the current understanding of intergalactic gas connections. Through this single spectral line, the invisible architecture of galaxy interactions becomes measurable, transforming diffuse hydrogen into a map of dynamical relationships across intergalactic space. Ultraviolet absorption line observations provide a fundamentally different way of detecting gas bridges, one that does not rely on the gas emitting light at all. Instead of searching for photons produced by the gas itself, this method detects gas by how it removes light from background sources. This approach is uniquely powerful for studying extremely diffuse structures, including large fractions of gas bridges that remain invisible even to sensitive radio surveys. Absorption line evidence has therefore become essential for understanding the full mass, composition, and extent of intergalactic gas connections. The basic strategy relies on bright background sources, most commonly quasars. Quasars are compact, extremely luminous objects powered by accretion onto supermassive black holes, and they emit intense radiation across a wide range of wavelengths, including the ultraviolet. When the light from a distant quasar passes through intervening gas on its way to Earth, atoms and ions along the line of sight absorb photons at very specific wavelengths. These absorbed wavelengths appear as narrow dips in the quasar's otherwise smooth spectrum. Each dip corresponds to a particular atomic transition, allowing the intervening gas to be identified and characterized even when it emits no detectable radiation of its own. Gas bridges are particularly well suited to this technique because they occupy large volumes of space with very low density. Even a tenuous column of gas can produce a detectable absorption feature if the background source is bright enough and the column density integrated along the line of sight is sufficient. Unlike emission, which scales with the square of the gas density, absorption scales linearly with column density. This difference is critical. Gas that is far too diffuse to glow can still leave a measurable imprint on background light, making absorption line spectroscopy the most sensitive probe of low-density baryonic matter in the universe. The most important absorption feature for detecting diffuse hydrogen is the Lyman alpha transition. This line arises when an electron in a neutral hydrogen atom absorbs a photon and transitions from the ground state to the first excited state. The Lyman alpha line lies in the ultraviolet and is therefore inaccessible from the ground due to absorption by Earth's atmosphere. Space-based ultraviolet telescopes are required to observe it. In spectra of background quasars, Lyman alpha absorption appears as a characteristic dip whose depth and width encode information about the column density, temperature, and velocity distribution of the intervening gas. Gas bridges often produce Lyman alpha absorption features that are broader and weaker than those associated with dense interstellar clouds. This reflects their low density and relatively high temperature. Thermal motion of hydrogen atoms broadens the absorption line, while low column density limits its depth. In many cases, multiple weak Lyman alpha absorbers appear clustered in velocity space, tracing extended structures rather than isolated clouds. When these absorbers occur at velocities consistent with interacting galaxies and are spatially aligned between them, they provide strong evidence for a diffuse gas bridge that may be only partially detected or entirely undetected in emission. Beyond hydrogen, absorption line spectroscopy reveals the presence of heavier elements, commonly referred to as metals in astronomical terminology. Transitions from ions of carbon, silicon, oxygen, and other elements appear at distinct ultraviolet wavelengths and provide crucial diagnostic information. These metal absorption lines serve several purposes. First, they confirm that the gas has been processed through stars, since heavy elements are produced by stellar nucleosynthesis. This establishes a galactic origin for the gas rather than a primordial one. Second, the relative strengths of different metal lines constrain the ionization state, temperature, and density of the gas. Carbon absorption lines, such as those arising from singly or doubly ionized carbon, are particularly useful tracers of warm, partially ionized gas. Silicon lines probe similar conditions but are sensitive to slightly different ionization parameters. Oxygen, especially in highly ionized states, traces hotter gas that may be interacting with galactic halos or shock-heated during the formation of the bridge. The simultaneous detection of multiple metal ions allows astronomers to construct ionization models that reveal whether the gas is primarily photoionized by ultraviolet radiation or collisionally ionized by high temperatures. Velocity information is embedded directly in absorption line spectra through Doppler shifts. Each absorption feature appears at a wavelength shifted according to the line-of-sight velocity of the gas relative to the observer. By comparing these velocities to the known systemic velocities and rotation curves of nearby galaxies, it becomes possible to associate absorption features with specific structures. Gas bridges exhibit velocity offsets that interpolate between the velocities of the interacting galaxies, mirroring the kinematic continuity seen in radio observations. This velocity coherence is a critical criterion for tying absorption features to bridges rather than to unrelated intergalactic gas. The power of this technique lies in its ability to detect gas that is otherwise completely invisible. Many regions of gas bridges fall below the column density thresholds required for 21 cm emission detection. In these regions, the neutral fraction may be low, or the gas may be highly ionized, rendering radio emission undetectable. Absorption, however, remains sensitive. A quasar sightline passing through even a small fraction of such gas can reveal its presence. As a result, absorption line studies often uncover extended envelopes of gas surrounding the denser cores detected in radio surveys, demonstrating that observed bridges represent only the densest parts of much larger structures. This sensitivity to diffuse gas connects gas bridges directly to the long-standing missing baryons problem. Measurements of the cosmic microwave background and primordial nucleosynthesis predict a specific abundance of baryonic matter in the universe. However, inventories of stars, cold gas, and hot gas in galaxies account for only a fraction of this expected baryon budget. A significant portion of baryonic matter is therefore considered missing not because it is absent, but because it is difficult to detect. Ultraviolet absorption line studies have shown that much of this missing baryonic matter resides in diffuse ionized gas distributed throughout galactic halos and intergalactic space. Gas bridges contribute to this reservoir. They represent regions where baryons are displaced from galaxies during interactions, but have not yet mixed fully into the intergalactic medium. Absorption line detections reveal that these bridges often contain large amounts of ionized gas with low density and high temperature, precisely the conditions expected for missing baryons. The connection becomes especially clear when absorption studies detect metal-enriched gas at large distances from galaxies. This enrichment demonstrates that baryons have been expelled or redistributed through galactic interactions, feedback, and tidal processes. Gas bridges serve as conduits for this redistribution, temporarily storing baryons outside galaxies while maintaining a physical and kinematic connection. Over time, this gas may be reaccreted, ionized further, or dispersed into the broader intergalactic medium, contributing to the diffuse baryon population traced by absorption lines. Absorption line evidence also provides insight into the three-dimensional structure of gas bridges. By observing multiple background quasars behind the same interacting system, astronomers can probe different sightlines through the bridge. Variations in absorption strength and ionization state across these sightlines reveal the internal structure of the gas, including clumpiness, gradients, and interfaces with surrounding halo gas. This tomographic approach is impossible with emission alone at current sensitivity levels and highlights the complementary nature of absorption and emission studies. The reliance on background quasars introduces limitations as well. Suitable quasars are rare, and their distribution on the sky is sparse. As a result, absorption line studies sample gas bridges along narrow pencil beam sightlines rather than mapping them continuously. Despite this limitation, the method remains indispensable because it accesses regimes of density and temperature that are otherwise unreachable. Each absorption detection represents a precise measurement of gas properties along a known line of sight, providing anchors for interpreting more spatially complete but less sensitive emission maps. Ultraviolet absorption line spectroscopy therefore expands the concept of a gas bridge beyond what is visible in radio data alone. It reveals bridges as multiphase structures containing neutral, warm, ionized, and sometimes hot ionized gas, much of which does not emit detectably at any wavelength. By linking absorption features to interacting galaxies through velocity and chemical signatures, this technique confirms that gas bridges are not marginal curiosities but significant reservoirs of baryonic matter. Through absorption, the space between galaxies is revealed as populated, structured, and dynamically active. Gas bridges emerge as important contributors to the baryon cycle, connecting galaxies not only gravitationally but chemically and thermodynamically. Their role in hosting diffuse ionized gas places them squarely within the broader context of the missing baryons problem, demonstrating that much of the universe's ordinary matter exists in forms that can be detected only by their subtle imprint on background light. The distinction between the intergalactic medium and the circumgalactic medium is fundamental to understanding where gas bridges exist and why they form. These two reservoirs of gas occupy different physical regimes, follow different dynamical rules, and play different roles in galaxy evolution. Gas bridges frequently emerge at the interface between them, occupying a transitional environment that reveals how galaxies interact with their surroundings and with each other. The intergalactic medium, commonly abbreviated as IgM, refers to the diffuse gas that fills the space between galaxies on large scales. It contains the majority of the universe's baryonic matter by volume, although not by density. The IgM is shaped primarily by the large-scale structure of the universe and the gravitational influence of dark matter filaments that span megaparsec distances. In this environment, gas is extremely tenuous. Typical particle densities are on the order of 1 particle per cubic meter or less, many orders of magnitude lower than even the most diffuse regions inside galaxies. Temperatures in the IgM vary widely. In cosmic filaments and sheets, gas often resides at temperatures of 10,000 to 100,000 Kelvin, maintained by photoionization from the cosmic ultraviolet background. In regions where filaments intersect or where shocks occur during structure formation, gas can be heated to millions of Kelvin, forming the warm-hot intergalactic medium. The circumgalactic medium, or CGM, occupies a very different regime. It is the extended gaseous envelope surrounding individual galaxies, bound within their dark matter halos. The CGM extends from the outer edge of the stellar disk to distances of several hundred kiloparsecs, often approaching the virial radius of the halo. Compared to the IGM, the CGM is denser and more dynamically complex. Typical densities range from 1/10,000th to 1/100th of a particle per cubic centimetre, depending on distance from the galaxy and the phase of the gas. Temperatures also span a broad range. Cool and warm gas phases near 10,000 Kelvin coexist with hot halo gas at temperatures of several million Kelvin, heated by gravitational infall, supernova feedback, and accretion shocks. The key distinction between the IGM and the CGM lies in gravitational binding and dynamical influence. Gas in the IGM is not bound to any single galaxy. Its motion is governed primarily by the gravitational potential of large-scale dark matter structures and the overall expansion of the universe. Gas in the CGM, by contrast, is gravitationally associated with a specific galaxy and its dark matter halo. Even when the gas is hot and diffuse, it remains dynamically coupled to the halo, participating in inflows, outflows, and recycling processes that regulate star formation. Gas bridges often form precisely where these two regimes meet. During a galaxy interaction, tidal forces and hydrodynamic effects strip gas from galactic disks and inner halos. This gas is displaced outward, but it does not immediately join the general IGM. Instead, it remains within the overlapping circumgalactic environments of the interacting galaxies. The result is a structure that is neither fully intergalactic nor fully circumgalactic. The bridge occupies the boundary region where the gravitational influence of both halos is significant, and where gas can be stretched, compressed, and heated without becoming completely unbound. This boundary location explains many observed properties of gas bridges. Their densities are lower than those typical of galactic disks, but higher than the average IGM. Their temperatures often reflect a mixture of phases, including cooler gas stripped from disks and hotter gas interacting with halo media. Ionization levels are elevated due to exposure to ultraviolet radiation from both galaxies and the cosmic background. These conditions are characteristic of the outer CGM rather than the IGM proper, reinforcing the idea that bridges are products of halo-scale interactions. Dark matter halos play a central role in shaping gas bridges. Each galaxy resides within a massive halo that dominates its gravitational potential out to hundreds of kiloparsecs. When two galaxies interact, their halos overlap long before their stellar disks come into contact. This overlap creates a complex gravitational landscape in which gas can be drawn out along preferred directions. The geometry of a gas bridge often reflects the shape and extent of the interacting halos rather than the visible distribution of stars. Gas responds more readily than stars to these extended gravitational fields because it is collisional and pressure-supported, allowing it to be stretched into long, continuous structures. The presence of dark matter halos also explains why gas bridges can span such large distances without being immediately dispersed. While the gas within a bridge is not self-bound, it remains confined within the combined potential of the interacting halos for a finite time. This confinement slows dispersal and allows the bridge to persist for hundreds of millions of years. Without the extended gravitational influence of dark matter halos, stripped gas would more quickly mix into the IGM and lose any coherent structure. The interaction between halos further affects the thermodynamic state of bridge gas. Hot halo gas exerts ram pressure on cooler, stripped material, shaping the morphology of the bridge and influencing its ionization state. Shock heating at the interface between different gas phases raises temperatures and can ionize large fractions of the gas. These processes are characteristic of the CGM environment and are largely absent in the low-density IGM. As a result, gas bridges often display properties that align more closely with circumgalactic gas than with truly intergalactic material. Gas bridges blur the definition of galaxy boundaries because they demonstrate that a galaxy's influence extends far beyond its visible stars. Traditionally, galaxies were defined by their stellar disks or spheroids, with sharp edges implied by optical images. The existence of extended gas bridges challenges this view. If gas stripped from one galaxy remains dynamically connected to another over distances of hundreds of kiloparsecs, then the effective boundary of a galaxy becomes ambiguous. The CGM itself already extends far beyond the stellar component, and bridges show that these extended halos can overlap and interact directly. This blurring of boundaries has important implications for how galaxies are classified and modelled. In isolation, a galaxy's CGM might be treated as a roughly spherical reservoir of gas. In group environments or interacting systems, however, CGMs become distorted, elongated, and interconnected. Gas bridges represent the most extreme manifestation of this interconnectedness. They demonstrate that galaxies do not evolve as isolated systems, but as members of a shared gaseous ecosystem shaped by overlapping halos and continuous gas exchange. The distinction between IGM and CGM also becomes observationally ambiguous in the presence of bridges. Absorption line studies often detect gas at distances where it is unclear whether the material should be classified as belonging to a galaxy's halo or to the general intergalactic medium. Velocity coherence and chemical enrichment provide clues, but the boundary remains fuzzy. Gas bridges occupy exactly this ambiguous regime, containing metal-enriched gas that originated in galaxies but now resides far outside their stellar bodies. From a theoretical perspective, gas bridges highlight the importance of treating galaxy evolution within a cosmological context. Dark matter halos are not isolated entities but parts of a larger network. When halos interact, their gaseous components respond in ways that are not captured by models that impose rigid boundaries. Bridges reveal that the CGM is dynamic, anisotropic, and responsive to environmental interactions. They also show that the IGM is continually influenced by processes occurring within galaxies, as stripped gas eventually mixes into the larger intergalactic reservoir. The existence of gas bridges therefore forces a re-evaluation of where galaxies end and intergalactic space begins. Rather than a sharp transition, there is a gradual change in density, temperature, and dynamical influence. Gas bridges sit within this transition zone, making them natural laboratories for studying the interplay between galactic and intergalactic processes. They trace how baryons move across scales, how dark matter halos shape gas geometry, and how the cosmic environment influences individual galaxies. In this context, the IGM and CGM should be viewed as interconnected components of a continuous baryonic medium. Gas bridges occupy the interface between them, revealing that the separation is conceptual rather than absolute. By studying bridges, it becomes clear that galaxies are not isolated islands embedded in empty space, but nodes within a complex, overlapping network of gas shaped by gravity, motion, and time. Tidal forces and orbital geometry govern the formation of gas bridges by determining how matter responds when two galaxies approach, interact, and move past one another. These processes operate over hundreds of millions of years and act most strongly on diffuse, pressure-supported components. Gas bridges therefore arise as natural outcomes of gravitational interactions when extended gaseous reservoirs experience differential forces that stretch, redirect, and temporarily connect material between galaxies. Differential gravity is the fundamental driver. When two galaxies approach, the gravitational field experienced by material on the near side of each galaxy differs from that experienced on the far side. This gradient in gravitational acceleration produces tidal forces that elongate structures along the line connecting the interacting systems. Gas, which is distributed over large radii in disks and halos, experiences these gradients across extended volumes. The result is a stretching of gas along preferred directions set by the interaction geometry. Because tidal forces scale with distance from the mass center, and with the mass of the perturber, gas at large galactocentric radii is particularly susceptible. Extended HI disks and circumgalactic gas respond first, forming elongated features that can bridge the gap between galaxies before stellar components are strongly affected. Gas responds differently from stars because of its physical state. Stars behave as collisionless particles. Each star follows an orbit determined primarily by gravity and conserves its phase space properties over long timescales. Gas, by contrast, is collisional and pressure supported. Gas clouds interact through collisions, shocks, and pressure gradients, allowing them to dissipate energy and change trajectories collectively. During an encounter, gas can lose orbital energy through shocks and radiative processes, enabling it to be redirected into coherent structures rather than simply flung outward on ballistic orbits. This dissipation allows gas to form continuous bridges, while stars tend to form discrete tidal tails or streams composed of individual orbits. The extended distribution of gas further enhances its susceptibility. Galactic gas disks and halos extend far beyond the bulk of the stellar mass, often reaching to tens or hundreds of kiloparsecs. These regions lie in shallower gravitational potentials and are less tightly bound. Tidal forces therefore act more effectively on gas than on stars, drawing it out along the interaction axis. In many interactions, gas bridges form even when the stellar disks show minimal distortion, emphasizing the sensitivity of gas to tidal perturbations. Orbital geometry plays a decisive role in determining whether a gas bridge forms and what shape it takes. The inclination of the orbital plane relative to the galactic disks influences how gas is stripped and stretched. Coplanar encounters, where the orbital plane aligns closely with one or both disks, tend to produce stronger, more symmetric tidal features. In such cases, gas can be drawn out efficiently along the line of centers, favoring bridge formation. Highly inclined or polar encounters distribute tidal forces differently, often producing warped or asymmetric structures and reducing the likelihood of a clean, continuous bridge. Pericenter distance, the closest approach between the interacting galaxies, sets the strength of tidal forces. Smaller pericenter distances produce stronger differential gravity and more dramatic gas redistribution. When galaxies pass within a few tens of kiloparsecs, tidal forces can strip large amounts of gas from outer disks and halos, feeding the formation of a bridge. Larger pericenter distances still produce tidal effects, but may result in weaker, more diffuse connections, or none at all. The mass ratio of the galaxies further modulates this effect, with more massive perturbers inducing stronger tides on less massive companions. Angular momentum redistribution is a central consequence of tidal interactions. During an encounter, gravitational torques transfer angular momentum between galaxies and between different components within each galaxy. Gas, because it can dissipate energy, responds efficiently to these torques. Angular momentum can be removed from gas in the outer disk, allowing it to move inward or outward, depending on the interaction geometry. In the context of bridge formation, angular momentum loss enables gas to flow toward the region between galaxies, forming a connecting structure rather than remaining bound to a single system. This redistribution is inherently asymmetric. Gas drawn into a bridge does not originate equally from both galaxies in most cases. Differences in mass, gas distribution, and orbital configuration determine which galaxy contributes more material. Velocity gradients along bridges often reflect this asymmetry, revealing a flow of gas that traces the angular momentum exchange during the encounter. These gradients provide observational evidence for the role of torques in shaping bridge kinematics. The formation of a gas bridge follows a characteristic timeline. During the initial approach, tidal forces begin to perturb the outer gas reservoirs of each galaxy. Subtle distortions appear in AGI distributions, often detectable only in sensitive radio observations. As the galaxies reach first pericenter passage, tidal forces peak. Gas is drawn out along the line connecting the galaxies, forming an elongated structure that links their extended halos. Shocks and compression occur where gas streams interact, influencing temperature and ionization state. Following first passage, the bridge becomes more clearly defined. The galaxies move apart, but the gas remains stretched between them, confined temporarily within the combined gravitational influence of their dark matter halos. During this phase, the bridge exhibits coherent velocity structure and can persist for hundreds of millions of years. The detailed morphology evolves as gas responds to ongoing tidal forces, pressure gradients, and interactions with hot halo gas. Dispersal begins as the galaxies continue along their orbits. The gravitational pull that initially confined the gas weakens as separation increases. Thermal pressure, turbulence, and ram pressure from surrounding halo gas act to disperse the bridge. Ionization increases, densities decrease, and the gas becomes progressively more diffuse. Portions of the bridge may fall back into one or both galaxies' circumgalactic media, while other fractions mix into the intergalactic medium. The transient nature of gas bridges follows directly from these processes. Bridges lack the mass and dark matter support required for long-term stability. Their existence depends on a specific alignment of gravitational forces during a limited phase of an interaction. Once that alignment changes, the bridge cannot maintain coherence. The same dissipative properties that allow gas to form a bridge also hasten its demise, as energy exchange with the environment erodes structure over time. Orbital evolution reinforces this transience. Galaxy encounters are dynamic events, not static configurations. Relative velocities, separations, and orientations evolve continuously, altering the tidal field experienced by the gas. A bridge that forms during one phase of the orbit may be stretched, twisted, or disrupted as the system evolves. Subsequent encounters, such as a second pericenter passage, can generate new bridges or destroy existing ones, depending on geometry and remaining gas supply. The role of tidal forces and orbital geometry highlights the importance of viewing gas bridges as dynamic phenomena rather than fixed structures. They encode detailed information about the interaction history of galaxies, including orbital parameters, mass distribution, and angular momentum exchange. By analysing bridge morphology and kinematics, astronomers can reconstruct aspects of past encounters that are otherwise difficult to infer. Gas bridges therefore represent a fleeting but informative stage in galaxy interactions. They arise when differential gravity acts on extended gas reservoirs under favourable orbital conditions, allowing dissipation and angular momentum transfer to create a temporary connection. Their eventual dispersal reflects the same physical principles as changing tidal fields and environmental interactions dissolve the structure. Through tidal forces and orbital geometry, gas bridges reveal how gravity sculpts diffuse matter across intergalactic space and how galaxies influence one another far beyond their visible boundaries. The Magellanic Bridge provides the most detailed and accessible example of a gas bridge in the nearby universe. It connects the large Magellanic Cloud and the small Magellanic Cloud, two interacting dwarf galaxies bound to each other and to the Milky Way. Unlike most known gas bridges, which are detected only as faint diffuse structures in distant systems, the Magellanic Bridge is close enough to be studied in exceptional detail across multiple wavelengths. Its proximity allows direct measurement of gas phases, kinematics, chemical composition, and even limited star formation, making it a benchmark for understanding how gas bridges form, evolve, and dissipate. Physically, the Magellanic Bridge spans a projected distance of roughly 20 kiloparsecs between the two galaxies, with its full extent reaching farther when diffuse components are included. In 3 dimensions, the structure is more complex, shaped by the relative motions of the clouds and their interaction with the Milky Way's halo. The bridge is composed primarily of neutral atomic hydrogen, forming a continuous distribution that links the outer gas envelopes of the two galaxies. Unlike many bridges observed in more massive galaxy pairs, the Magellanic Bridge is relatively narrow and well-defined, with a clear spatial alignment along the line connecting the clouds. The gas distribution within the bridge is highly structured. Radio observations reveal clumps, filaments, and density enhancements embedded within a more diffuse background. These structures reflect the turbulent history of the gas, shaped by tidal stretching, compression, and interaction with surrounding halo material. The bridge does not form a smooth, uniform filament. Instead, it shows significant variation in column density along its length, with denser regions closer to the parent galaxies and more diffuse gas toward the central span. Estimates of the total gas mass in the Magellanic Bridge indicate a substantial reservoir of baryonic material. Neutral hydrogen alone accounts for tens of millions of solar masses, placing the bridge among the most massive known intergalactic gas connections between dwarf galaxies. When ionized gas is included, the total gas mass increases significantly, potentially rivaling or exceeding the neutral component. This multi-phase nature highlights a key lesson from the Magellanic system. Emission-based measurements capture only part of the baryonic content, while absorption and modelling reveal a much larger, partially hidden mass. The velocity structure of the Magellanic Bridge provides some of the clearest evidence that it is a genuine dynamical connection rather than a chance alignment. High-resolution 21-centimetre observations show a continuous velocity gradient extending from the systemic velocity of the large Magellanic Cloud to that of the small Magellanic Cloud. This gradient is smooth rather than abrupt, indicating that the gas forms a single coherent structure responding to a shared gravitational interaction. The velocities also reflect the relative orbital motion of the two galaxies, encoding information about their past encounter. Velocity dispersion within the bridge is modest compared to that of galactic disks, but elevated relative to quiescent interstellar gas. This reflects a combination of thermal motion, turbulence induced by tidal forces, and interactions with the surrounding halo. Localized regions of higher dispersion often coincide with density enhancements, suggesting sites of compression or shock interaction. These kinematic features distinguish the Magellanic Bridge from isolated gas clouds and confirm its origin in a large-scale dynamical process. The origin of the Magellanic Bridge has been debated extensively, with two primary mechanisms considered: tidal stripping and ram pressure effects. Tidal forces arise from the mutual gravitational interaction between the large and small Magellanic Clouds during close passages. Numerical simulations demonstrate that such encounters can naturally draw gas out of the outer regions of the galaxies, stretching it into a bridge-like structure aligned with their orbital geometry. The continuity of the velocity field and the chemical similarity of the gas to the parent galaxies strongly support a tidal origin. Ram pressure contributes in a secondary but non-negligible way. As the Magellanic Clouds move through the hot, gaseous halo of the Milky Way, they experience pressure that can strip gas from their outer regions. This effect is particularly relevant for the small Magellanic Cloud, which has a shallower gravitational potential and is more vulnerable to gas removal. Ram pressure can enhance tidal stripping by lowering the effective binding energy of the gas, making it easier for tidal forces to extract material. In the Magellanic Bridge, observational signatures such as asymmetric gas distributions and ionization gradients suggest that ram pressure has modified the bridge after its initial formation. The balance between tidal and ram pressure processes explains several observed properties of the bridge. Tidal forces account for the coherent structure and velocity continuity, while ram pressure helps explain the elevated ionization levels and the gradual erosion of the bridge over time. This combination of mechanisms is likely common in satellite systems embedded within the halos of larger galaxies, making the Magellanic Bridge a prototype for bridges in group environments. One of the most distinctive features of the Magellanic Bridge is the presence of star formation. Although sparse and localized, young stars and stellar associations have been identified within the bridge. This is unusual, as most gas bridges lack the density and cooling conditions required for star formation. In the Magellanic case, several factors converge to allow limited star formation to occur. The gas density in parts of the bridge is higher than in typical intergalactic connections, and the metallicity, while lower than in the Milky Way, is sufficient to enable radiative cooling through metal lines. Compression plays a critical role. Tidal stretching does not simply dilute gas uniformly. It can also create regions of convergence where gas streams intersect or are compressed by external pressure. In the Magellanic Bridge, such compression is enhanced by interaction with the Milky Way's halo, which can confine gas and increase local density. These conditions allow small pockets of gas to cool, fragment, and form stars, even though the overall environment remains hostile to widespread star formation. The stars formed in the bridge are typically young and low mass, reflecting the limited and transient nature of the star-forming regions. Their spatial distribution traces the densest gas clumps rather than the bridge as a whole. This localized star formation provides direct evidence that, under the right conditions, even diffuse intergalactic gas can briefly cross the threshold required for gravitational collapse. The unusually high density of the Magellanic Bridge compared to other gas bridges can be attributed to the specific properties of the interacting galaxies and their environment. Both Magellanic clouds are gas-rich dwarf galaxies with extended high envelopes that provide ample material for stripping. Their relative masses and orbital configuration favour efficient tidal interaction, while their motion through the Milky Way's halo adds an external pressure component that limits excessive expansion of the stripped gas. The proximity of the two galaxies also matters. The distance between the large and small Magellanic clouds during their closest approach was relatively small, producing strong tidal forces over a compact region. This contrasts with many galaxy pairs where larger separations and higher relative velocities result in more diffuse, lower-density bridges. In the Magellanic system, the combination of strong tides, abundant gas supply, and environmental confinement creates a bridge that is denser, more coherent, and longer-lived than most. Chemical evidence further supports this picture. Measurements of metallicity along the bridge show values intermediate between those of the two galaxies, consistent with gas originating from their outer regions. This enrichment level aids cooling and distinguishes the bridge gas from primordial intergalactic material. The preservation of these chemical signatures indicates that the bridge has not yet fully mixed with the surrounding intergalactic medium, reinforcing its interpretation as a recently formed, dynamically connected structure. The Magellanic Bridge therefore serves as a crucial case study for gas bridges more generally. Its physical properties demonstrate how tidal forces can draw gas out of galaxies, how orbital geometry shapes large-scale structure, and how environmental effects modify evolution. Its measurable gas mass and velocity structure provide direct evidence for coherent intergalactic connections, while its limited star formation illustrates the extreme conditions required for stars to form outside galaxies. By studying the Magellanic Bridge in detail, astronomers gain insight into processes that operate throughout the universe but are usually hidden by distance and low surface brightness. The bridge shows that gas bridges are not abstract theoretical constructs, but real, measurable structures that influence galaxy evolution. It also reveals that under favourable conditions, these structures can briefly become sites of star formation, blurring the traditional boundary between galaxies and the space between them. Ram pressure plays a decisive role in shaping, ionizing, and ultimately eroding gas bridges once they form. While tidal forces create the initial connection by stretching gas between galaxies, ram pressure governs how that gas evolves as it moves through a surrounding medium. This process is especially important in environments where galaxies are embedded in extended, hot, gaseous halos, such as galaxy groups and massive spirals. In these settings, gas bridges do not evolve in isolation, but are continuously modified by their motion through a diffuse, high-temperature plasma. Hot galactic halos are a defining feature of massive galaxies. Surrounding many galaxies is an extended envelope of ionized gas at temperatures of millions of Kelvin, supported by the galaxy's dark matter halo. This hot medium, often referred to as halo gas, fills the circumgalactic region out to hundreds of kiloparsecs. Although extremely diffuse, it exerts pressure on any cooler gas moving through it. When a gas bridge passes through this environment, it experiences ram pressure proportional to the density of the halo gas and the square of the relative velocity between the bridge and the surrounding medium. The physical interaction between a gas bridge and a hot halo begins with compression. As the bridge moves through the halo, gas on the leading side encounters resistance. This resistance compresses the gas, raising its density locally, while simultaneously increasing its temperature through shock heating. Compression can temporarily enhance detectability by increasing column density, but it also accelerates ionization and heating. The balance between these effects determines whether a bridge becomes more prominent or begins to fade. Heating occurs through several mechanisms. Shocks form where the relative velocity between the bridge gas and halo gas exceeds the local sound speed. These shocks convert kinetic energy into thermal energy, raising temperatures from tens of thousands of Kelvin to hundreds of thousands or even millions of Kelvin. Thermal conduction across the interface between hot halo gas and cooler bridge gas further transfers energy into the bridge. In addition, turbulent mixing layers develop at the boundary, blending hot and cool gas and raising the ionization state of the material. Stripping is a direct consequence of these processes. Ram pressure acts to remove gas from the bridge, particularly from regions of lower density. Unlike tidal stripping, which depends on gravitational gradients, ram pressure stripping depends on motion through a medium. Gas that is loosely bound within the bridge can be peeled away, leaving behind a narrower, more ionized structure. Over time, this stripping reduces the total gas mass of the bridge and disrupts its coherence. Relative velocity is a critical parameter in determining bridge morphology under ram pressure. Faster motion through a halo produces stronger ram pressure, leading to more efficient compression and stripping. In such cases, bridges often develop asymmetric morphologies, with a denser leading edge and a trailing wake of more diffuse, ionized gas. Slower relative velocities allow gas to remain cooler and denser for longer periods, preserving neutral components and extending the bridge's lifetime. The direction of motion also matters. If a bridge moves roughly perpendicular to its long axis, ram pressure acts uniformly across its width, producing a relatively smooth compression. If motion occurs along the bridge axis, ram pressure can stretch and fragment the structure, creating knots and filaments aligned with the flow. These geometric effects imprint characteristic shapes that can be used to infer relative motion and environmental conditions. Ionization fronts provide some of the clearest observational signatures of ram pressure interaction. As gas is heated and ionized, sharp transitions can form between neutral and ionized regions. These fronts often appear as abrupt drops in neutral hydrogen column density, accompanied by enhanced ionized gas signatures. In some cases, the ionized gas becomes detectable through ultraviolet absorption lines of highly ionized species, indicating temperatures far above those typical of purely tidal structures. Such ionization fronts mark the progressive transformation of a gas bridge. Initially dominated by neutral atomic hydrogen, the bridge gradually shifts toward a warm or hot ionized state. Once the neutral fraction drops below detectability thresholds, the bridge effectively disappears from radio observations, even though substantial amounts of gas may remain present in ionized form. This transition explains why some interacting systems show evidence of past connections without a clearly detectable high bridge. The tendency for some bridges to become mostly ionized reflects a combination of environmental exposure and intrinsic fragility. Bridges formed in dense halo environments experience sustained heating and ionization. Ultraviolet radiation from nearby galaxies and the cosmic background further maintains ionization. Without efficient cooling pathways, the gas remains ionized and diffuse. Over time, the bridge fades observationally, transitioning from a radio-bright structure to an absorption-only or entirely undetectable feature. Motion through a hot halo significantly shortens bridge lifetime. Tidal forces alone might allow a bridge to persist for several 100 million years, confined within overlapping dark matter halos. Ram pressure accelerates dispersal by removing gas, heating it, and increasing turbulence. The combined effect reduces coherence and drives mixing with the surrounding halo gas. In extreme cases, bridges can be disrupted on timescales of tens to a few 100 million years, far shorter than would be expected from gravitational considerations alone. The fate of stripped gas depends on local conditions. Some gas is reaccreted into the circumgalactic medium of one or both galaxies, contributing to halo enrichment. Other fractions mix into the intergalactic medium, becoming part of the diffuse ionized baryon reservoir. In both cases, the original bridge structure is lost, replaced by a more isotropic distribution of ionized gas. Ram pressure also influences star formation prospects within bridges. Compression can raise density locally, but the accompanying heating and turbulence generally inhibit cooling. In most environments, ram pressure suppresses star formation by maintaining high temperatures and preventing long-lived dense clumps from forming. This effect explains why star-forming bridges are rare and typically associated with unusually dense or shielded environments. The combined action of tidal forces and ram pressure highlights the complexity of gas bridge evolution. Tides create structure by redistributing gas under gravity, while ram pressure reshapes and erodes that structure through interaction with hot halos. Bridges therefore encode information not only about galaxy-galaxy interactions, but also about the gaseous environments in which those interactions occur. Observationally, the imprint of ram pressure can be identified through asymmetries in gas distribution, gradients in ionization state, elevated temperatures, and the presence of highly ionized species detected in absorption. These signatures distinguish bridges evolving in dense halos from those in more isolated environments. By comparing systems across different environments, astronomers can assess how halo gas density and relative velocity influence bridge survival. Ram pressure shaping emphasizes that gas bridges are environmentally sensitive phenomena. Their appearance, composition, and longevity depend not only on the interacting galaxies, but also on the properties of the medium they traverse. Motion through a hot halo transforms bridges from neutral, detectable structures into diffuse, ionized remnants that fade from view. This process reinforces the transient nature of gas bridges and underscores their role as brief but informative phases in the circulation of baryons between galaxies and the larger cosmic environment. Gas bridges between galaxy pairs provide direct evidence that interactions do more than distort morphology. They enable the physical transfer of baryonic matter from one system to another. In nearby galaxy pairs, where spatial resolution and sensitivity are sufficient to trace diffuse gas in detail, bridges appear as extended reservoirs of neutral and ionized hydrogen connecting the outer regions of the galaxies. These structures are most clearly observed in radio surveys of atomic hydrogen, often extending well beyond the stellar disks and linking the galaxies across tens or even hundreds of kiloparsecs. Unlike tidal tails, which typically curve away from the interacting pair, gas bridges occupy the region between galaxies, signaling that material is not simply being ejected but redistributed within the shared gravitational environment. Observations of nearby interacting pairs show that gas bridges are common when galaxies experience close passages with favorable orbital geometry. In spiral-spiral interactions, bridges often emerge from the outer high disks, where gas is weakly bound and easily perturbed. In spiral dwarf or dwarf-dwarf pairs, bridges can dominate the observable intergalactic gas content because the galaxies themselves are gas-rich and dynamically fragile. High-sensitivity surveys reveal that these bridges are rarely uniform. Instead, they show gradients in column density, temperature, and velocity, all of which provide clues about the direction and efficiency of gas transfer. One of the most important insights from kinematic studies is that gas flow along bridges is often directional. Velocity maps constructed from the 21 centimetre line show that gas velocities change smoothly along the bridge, but not symmetrically. In many systems, velocities indicate net inflow toward one galaxy rather than balanced exchange. The gas may originate primarily from the outer disk of one galaxy and move along the bridge toward its companion, where it slows, compresses, and may eventually be accreted. This preferential flow is revealed by velocity gradients that steepen near the receiving galaxy and by asymmetries in gas density along the bridge. The evidence for directional flow is strengthened by comparing gas kinematics with stellar dynamics. While stars in tidal features often display broad velocity dispersions and complex orbital patterns, gas in bridges tends to follow a more ordered velocity field. This coherence reflects the dissipative nature of gas. Shocks and collisions allow gas to lose orbital energy and angular momentum, enabling it to drift toward a gravitational potential minimum. As a result, gas bridges often act as conduits funneling material toward the galaxy with a deeper potential well, rather than as static links between equals. Mass transfer rates inferred from observations span several orders of magnitude, depending on the mass of the galaxies involved, the density of the bridge, and the interaction stage. In modest interactions between dwarf galaxies, transfer rates may be as low as a few hundredths of a solar mass per year. In more massive spiral-spiral encounters, especially those approaching merger conditions, rates can reach 1 solar mass per year or more. Even the lower end of this range is significant on galactic timescales. Sustained over a few 100 million years, such transfer can move millions of solar masses of gas from one galaxy to another. These mass transfer rates are estimated by combining column density measurements with velocity information and assumptions about bridge geometry. While uncertainties remain, the orders of magnitude are robust enough to demonstrate that gas bridges can materially alter the gas budgets of galaxies. A donor galaxy may lose a substantial fraction of its outer gas reservoir, while the recipient galaxy gains fresh material that can influence its subsequent evolution. This exchange is particularly important for galaxies that would otherwise exhaust their internal gas supplies and experience declining star formation. The arrival of bridge gas can rejuvenate star formation in the receiving galaxy through several mechanisms. Inflowing gas increases the total gas mass and surface density, especially in the outer disk or inner halo. As gas settles into rotational equilibrium, it can cool, fragment, and join existing star-forming regions. In some cases, inflow triggers enhanced star formation by compressing pre-existing gas, lowering the stability threshold for gravitational collapse. This process does not necessarily produce starbursts, but it can sustain moderate star formation rates for longer periods than would be possible in isolation. Rejuvenation effects are often subtle and distributed rather than dramatic. Instead of creating luminous starburst regions, bridge-fed accretion may maintain extended, low-level star formation across a disk. This is particularly relevant for galaxies in group environments, where repeated interactions and gas exchange can prolong star formation over cosmic time. Gas bridges thus contribute to the regulation of star formation histories by redistributing baryons within galaxy populations. The gas exchange process is inherently asymmetric, and this asymmetry arises from fundamental physical differences between the interacting galaxies. Mass is a primary factor. The galaxy with the deeper gravitational potential exerts stronger tidal forces and is more effective at capturing gas. Orbital geometry also plays a role. If one galaxy approaches on a prograde orbit relative to the other's disk rotation, tidal coupling is enhanced, favouring gas removal from the prograde disk and accretion by the companion. Retrograde encounters are less efficient at producing strong, directed flows. Angular momentum differences further amplify asymmetry. Gas stripped from a galaxy carries angular momentum inherited from its original orbit. Through shocks and dissipation within the bridge, this angular momentum can be redistributed or lost, allowing gas to fall inward toward the receiving galaxy. The efficiency of this process depends on how well the gas can radiate energy and how strongly it interacts with the surrounding medium. These conditions are rarely symmetric between two galaxies, leading to preferential accretion. Environmental factors also contribute. If one galaxy resides in a denser circumgalactic environment or within a larger halo, ram pressure and halo confinement can help capture incoming gas. The donor galaxy, especially if it is less massive, may lose gas more easily and be less able to reaccrete it. Over time, repeated asymmetric exchanges can significantly alter the relative gas fractions and evolutionary paths of the galaxies involved. Stars rarely follow the gas during these exchanges because they obey fundamentally different dynamical rules. Stars are collisionless and cannot dissipate energy through shocks or radiation. When subjected to tidal forces, stars are redistributed along ballistic orbits that conserve energy and angular momentum. This leads to the formation of stellar tidal tails and streams rather than coherent inflows. Once a star is stripped from its parent galaxy, it continues along an orbit determined by the gravitational potential, with little opportunity to lose energy and fall into another galaxy. Gas, by contrast, is collisional and dissipative. Collisions between gas clouds, shocks induced by differential motion, and interactions with hot halo gas all allow gas to shed energy. This energy loss enables gas to change orbits and move inward within a gravitational potential. The same processes that allow gas to form bridges also allow it to be captured, compressed, and eventually incorporated into a galaxy's interstellar medium. This fundamental difference explains why gas bridges are efficient channels for baryonic exchange, while stars remain largely confined to their original systems or disperse into long-lived streams. The separation between gas and stars in these interactions has important observational consequences. A galaxy may gain gas and experience renewed star formation without acquiring a corresponding stellar population from its companion. Conversely, a galaxy may lose gas while retaining most of its stars, leading to quenching over time. Gas bridges, therefore, decouple the evolution of stellar mass and gas mass, allowing interactions to reshape galaxies in ways that are not immediately obvious from their stellar appearance alone. In nearby galaxy pairs, this decoupling is directly observable. Stellar disks may appear relatively undisturbed, while extended high-maps reveal dramatic bridges and gas flows. This discrepancy underscores the importance of multi-wavelength observations in understanding galaxy evolution. Gas bridges capture processes that are invisible in optical light, but central to the redistribution of matter and the regulation of star formation. Gas exchange through bridges also has cumulative effects. Over multiple interactions, a galaxy may act alternately as donor and recipient, depending on encounter geometry and relative mass. In group environments where interactions are frequent, bridges can facilitate a continuous circulation of gas among members. This circulation redistributes metals, alters gas fractions, and influences the timing and location of star formation across the group. Viewed in this context, gas bridges are not rare curiosities but integral components of galactic ecosystems. They provide a mechanism for transferring mass, energy, and angular momentum between galaxies without requiring mergers. Their asymmetric nature reflects the underlying asymmetries of gravitational potentials and orbital configurations. Their effectiveness depends on the dissipative properties of gas, which allow it to behave in ways fundamentally different from stars. Through gas bridges, galaxy pairs engage in a form of baryonic exchange that reshapes their evolution over hundreds of millions of years. The process fuels star formation in some systems, deprives others of gas, and leaves stellar structures largely untouched. This selective redistribution of matter highlights the central role of gas dynamics in galaxy evolution and illustrates why interactions must be understood not only in terms of stars and morphology, but also in terms of the hidden flows of diffuse gas connecting galaxies across intergalactic space. Star formation in gas bridges occupies one of the most extreme regimes in astrophysics. These environments sit far outside the conditions normally associated with star formation, characterized by very low densities, elevated temperatures, strong tidal shear, and continuous external heating. Yet in a small number of cases, stars do form. Understanding why this happens only rarely and under what conditions requires examining the fundamental physics of gravitational collapse and how it is modified in diffuse intergalactic gas. The starting point for any discussion of star formation is gravitational instability, commonly described through the Jeans criterion. For a parcel of gas to collapse under its own gravity, its self-gravitational energy must exceed the opposing effects of thermal pressure and internal motions. The Jeans scale sets a critical mass and size above which collapse becomes possible. In gas bridge environments, this criterion is almost never satisfied. Densities are typically several orders of magnitude lower than those in galactic disks, while temperatures are significantly higher. Both effects act in the same direction. They increase the Jeans mass to values far larger than any coherent gas clump that can realistically form within a bridge. In practical terms, this means that a region of gas in a bridge would need to accumulate an enormous mass within a relatively small volume to become gravitationally unstable. At densities of 1/10,000th of a particle per cubic centimetre or less, and temperatures around 10,000 Kelvin, the Jeans mass can exceed millions of solar masses. Such conditions are incompatible with the fragmented filamentary structure of most bridges. Instead of collapsing, gas responds to perturbations by expanding, dispersing, or being stretched further by tidal forces. Thermal pressure is only part of the problem. Gas bridges also experience significant turbulence and shear. Relative motion between different parts of the bridge, induced by tidal stretching and interactions with surrounding halo gas, injects kinetic energy into the gas. This turbulent support acts like an additional pressure term, further stabilizing the gas against collapse. Even if a local overdensity begins to form, turbulent motions can disrupt it before gravity becomes dominant. External heating reinforces this stability. Ultraviolet radiation from nearby galaxies and the cosmic background maintains ionization and keeps gas temperatures high. Shock heating from ram pressure and halo interactions injects additional energy. Cooling times in such environments are often longer than the dynamical timescales over which the bridge evolves. Without efficient cooling, gas cannot shed thermal energy and condense into cold, dense phases required for star formation. As a result, most gas in bridges never collapses. It remains in a diffuse, warm, or ionized state throughout the lifetime of the structure. Density fluctuations that arise from tidal compression or turbulence are typically transient. They are stretched apart by shear, heated by radiation, or stripped away by ram pressure before they can evolve into bound clouds. This explains why the vast majority of gas bridges are completely devoid of stars, despite containing large amounts of baryonic material. Nevertheless, observations have revealed a small number of star clusters embedded within certain gas bridges. These clusters are rare, localized, and typically low in mass. Their existence demonstrates that under specific circumstances, gas in bridges can briefly cross the threshold required for star formation. Studying these exceptions provides insight into the conditions that allow collapse in otherwise hostile environments. Observed star clusters in bridges tend to be associated with regions of enhanced gas density. These enhancements are not random, but often coincide with sites of compression. Compression can arise from converging gas flows within the bridge, tidal squeezing during close passages, or interaction with external pressure from hot halo gas. When gas is compressed faster than it can re-expand or be heated, density can rise sufficiently to reduce the local Jeans mass. Cooling pathways play a decisive role at this stage. Even modest cooling can lower gas temperature, dramatically reducing the gene's mass and enabling collapse. In bridge environments, the most important cooling mechanisms involve atomic line emission from hydrogen and heavier elements. At temperatures around 10,000 Kelvin, cooling through hydrogen line emission is relatively inefficient. The presence of metals becomes critical. Metal ions provide additional energy levels that allow gas to radiate energy more effectively, accelerating cooling and promoting condensation. Metallicity therefore matters enormously for star formation in bridges. Gas stripped from galactic disks or inner halos carries a chemical imprint of past star formation, including elements heavier than helium. Even low metallicity gas can cool orders of magnitude more efficiently than primordial gas composed only of hydrogen and helium. In bridges with higher metallicity, cooling times can become short enough for gas to transition into colder phases before being disrupted. This dependence on metallicity explains why star formation in bridges is observed primarily in systems involving gas-rich galaxies with prior star formation histories. Bridges formed from chemically enriched outer disks are far more likely to host localized star formation than those composed of pristine or highly ionized gas. It also explains why star formation is unevenly distributed along a bridge, confined to regions where metallicity and density align favorably. Dust, while scarce in bridges, also contributes indirectly. Even small amounts of dust can enhance cooling and provide shielding from ultraviolet radiation, allowing pockets of gas to remain neutral and cool. In the densest regions, this shielding can create microenvironments that resemble the outer edges of galactic molecular clouds, albeit on much smaller scales. These pockets are fragile and short-lived, but they can persist long enough for stars to form. The star clusters that emerge in these environments differ from those formed in galactic disks. They are often loosely bound, low mass, and sparsely populated. Their formation efficiency is extremely low, meaning that only a tiny fraction of the available gas is converted into stars. Feedback from even a small number of young stars can rapidly disrupt the surrounding gas, halting further star formation and leaving the cluster isolated within a diffuse medium. Comparing star formation in gas bridges to that in tidal dwarf galaxies highlights important contrasts. Tidal dwarf galaxies form in the dense ends of tidal tails, produced during major galaxy interactions. These environments, while still perturbed, are far more favourable for star formation than gas bridges. Densities are higher, cooling is more efficient, and the gravitational potential of the accumulating gas can become self-sustaining. As a result, tidal dwarf galaxies can host sustained star formation and develop into long-lived stellar systems. Gas bridges lack these advantages. Their gas is spread over larger volumes, subjected to stronger shear, and deprived of the gravitational confinement needed to stabilize dense regions. While tidal dwarf galaxies can become self-gravitating entities, gas bridges remain dependent on external potentials and pressures. Star formation within bridges therefore represents isolated events rather than the emergence of new galaxies. The difference is also reflected in kinematics. Gas in tidal dwarf galaxies often shows signs of rotational support and coherent internal motion indicative of a bound system. Gas in bridges, by contrast, is dominated by bulk flows along the bridge axis and by external forces. Any stars that form inherit these motions, resulting in clusters that may disperse over time rather than remaining bound indefinitely. The rarity of star formation in bridges reinforces the idea that star formation is not a universal outcome of gas presence, but a consequence of specific physical conditions. High gas mass alone is insufficient. Density, temperature, metallicity, shielding, and dynamical stability must all align. In bridges, these conditions align only fleetingly and locally. From a broader perspective, star formation in extreme low-density gas provides a valuable test of star formation theory. It probes the limits of gravitational instability and cooling in environments far removed from the conditions under which most stars form. Observations of bridge star clusters challenge models to account for star formation in regimes where traditional assumptions break down. These rare events also carry implications for galaxy evolution. Even minimal star formation in bridges can contribute to the redistribution of stellar populations and metals on large scales. Stars formed outside galaxies may later be accreted or dispersed into halos, adding complexity to the stellar content of galaxies and their surroundings. Ultimately, gas bridges demonstrate that star formation is possible even in the most unlikely places, but only under narrowly defined conditions. The dominance of stabilizing forces ensures that most gas remains diffuse and inert. When collapse does occur, it does so briefly, locally, and inefficiently. By comparing these environments to more favorable sites, such as tidal dwarf galaxies, it becomes clear that star formation in bridges represents the extreme edge of the star formation parameter space, illuminating both the robustness and the limits of the physical processes that turn gas into stars. Chemical composition provides one of the most powerful diagnostics for understanding the origin, evolution, and fate of gas bridges. While morphology and kinematics reveal how gas is arranged and moving, chemical fingerprints reveal where that gas came from, what it has experienced, and how recently it was removed from its parent system. Because chemical abundances change only through well-defined physical processes, they act as long-lived tracers that preserve information long after dynamical structures begin to disperse. Metallicity, the abundance of elements heavier than helium, is the primary chemical quantity measured in gas bridges. In practice, metallicity is inferred through spectroscopy, using emission or absorption lines of heavy elements such as oxygen, carbon, nitrogen, silicon, and iron. In neutral and weakly ionized gas, ultraviolet absorption line spectroscopy is particularly effective, while in denser or partially ionized regions, optical and ultraviolet emission lines can also be used. By measuring the relative strengths of these lines and correcting for ionization effects, astronomers can estimate elemental abundances along different regions of a bridge. One of the most striking chemical features observed in gas bridges is the presence of metallicity gradients along their length. These gradients typically show higher metallicity near one or both parent galaxies, with a gradual decline toward the central or more distant regions of the bridge. Such patterns reflect the original radial metallicity gradients within galactic disks or halos, where inner regions are more chemically enriched due to prolonged star formation, while outer regions are more metal-poor. When gas is tidally stripped, it carries this gradient with it, effectively mapping the chemical structure of the parent galaxy into intergalactic space. The detection of these gradients provides strong evidence that bridge gas originates from galaxies rather than from pristine intergalactic material. If a bridge were composed primarily of primordial gas drawn from the intergalactic medium, its metallicity would be extremely low and relatively uniform. Instead, observed bridges often exhibit metallicities comparable to the outer disks or halos of galaxies, sometimes reaching a significant fraction of the solar value. This enrichment demonstrates that the gas has been processed through multiple generations of stars before being displaced into the bridge. Chemical gradients also help identify which galaxy contributed most of the gas. In interacting pairs with different metallicities, the bridge often shows values that match one galaxy more closely than the other. For example, if one galaxy has a systematically lower metallicity due to its mass or star formation history, and the bridge shares this lower metallicity, the inference is that the bridge gas was stripped primarily from that system. In some cases, metallicity varies asymmetrically along the bridge, revealing contributions from both galaxies and allowing reconstruction of the interaction geometry. Evidence for chemical mixing between galaxies appears when metallicity patterns deviate from simple extrapolations of a single galaxy's gradient. In some bridges, intermediate metallicities are observed that cannot be explained solely by stripping from one disk. These values indicate that gas from both galaxies has mixed within the bridge. Mixing can occur through turbulent flows, shocks, and shear as gas streams interact and overlap. Over time, this mixing smooths out sharp chemical contrasts, producing a more homogeneous composition that reflects contributions from multiple sources. The presence of mixed gas has important implications. It shows that gas bridges are not merely passive structures, but active sites of interaction where material from different galaxies can combine. This mixing redistributes metals on intergalactic scales and alters the chemical environment of both galaxies once the gas is reaccreted or dispersed. In group environments, repeated interactions and bridges can gradually homogenize the chemical composition of circumgalactic gas across multiple systems. Beyond overall metallicity, detailed elemental abundance ratios provide deeper insight into the history of bridge gas. Different elements are produced by different types of stars on different timescales. For example, oxygen and other alpha elements are produced primarily by massive stars and released quickly through core collapse supernovae, while iron is produced in significant quantities by type Ia supernovae on longer timescales. The ratio of alpha elements to iron therefore encodes information about the duration and intensity of past star formation. Measurements of these abundance ratios in bridge gas often resemble those found in the outer regions of galactic disks or halos. This similarity indicates that the gas was removed after experiencing a specific chemical enrichment history rather than being primordial or recently accreted from the intergalactic medium. In some cases, abundance ratios suggest that the gas was stripped before the full contribution of type Ia supernovae, implying removal relatively soon after episodes of star formation. In others, more iron-rich compositions indicate longer enrichment histories. Isotopic abundances, while more challenging to measure, provide additional constraints. Certain isotopes are sensitive to specific nucleosynthetic pathways and stellar populations. Although direct isotopic measurements are rare in diffuse bridge gas, indirect constraints from molecular species and fine structure lines can sometimes be obtained in denser regions. These constraints further support a galactic origin and help distinguish between gas stripped from disks, gas expelled by feedback, and gas accreted from the intergalactic medium. Chemical signatures also reveal the degree to which bridge gas has been altered since its removal. If the gas had undergone significant in situ star formation or prolonged mixing with the intergalactic medium, its chemical composition would evolve accordingly. The fact that many bridges retain metallicities and abundance patterns closely matching their parent galaxies indicates that such processing has been limited. This preservation of original chemical properties suggests relatively short lifetimes and inefficient star formation within bridges. The ability of bridges to preserve chemical memory arises from several factors. First, low densities suppress star formation, limiting the production of new metals within the bridge itself. Second, mixing with the surrounding intergalactic medium is slow, particularly when the bridge remains confined within overlapping circumgalactic halos. Third, the timescales for significant chemical evolution are longer than the typical lifetime of a bridge. As a result, the gas retains the chemical imprint it had at the moment of stripping. This preserved chemical memory allows gas bridges to function as time capsules of galactic evolution. By studying their composition, astronomers can infer conditions in galactic outskirts at the time of interaction, including metallicity gradients, enrichment timescales, and feedback efficiency. Bridges therefore provide complementary information to that obtained from stars, which may have migrated or evolved since their formation. Chemical fingerprints also help distinguish between different formation mechanisms. Tidal stripping tends to remove gas from specific regions of a galaxy, preserving radial gradients and characteristic abundance ratios. Ram pressure stripping, by contrast, can remove gas more selectively based on density and binding energy, potentially biasing the chemical composition of the stripped material. By comparing observed chemical patterns with predictions from simulations, it becomes possible to assess the relative importance of these mechanisms in individual systems. The implications extend beyond individual interactions. On cosmological scales, chemical measurements of bridge gas contribute to understanding how metals are redistributed throughout the universe. Gas bridges represent a pathway by which metals produced in galaxies are transported into halos and eventually into the intergalactic medium. This redistribution influences the chemical evolution of the IGM and affects cooling and star formation in later generations of galaxies. Chemical studies of bridges also inform models of galaxy growth. If a galaxy accretes gas from a bridge with a particular metallicity, that gas will alter the chemical composition of its interstellar medium and influence subsequent star formation. Repeated episodes of gas exchange can therefore shape metallicity gradients, stellar populations, and feedback cycles over long timescales. In this context, gas bridges emerge as chemically informative structures that bridge not only physical space but evolutionary histories. Their compositions encode the past star formation activity of galaxies, the dynamics of interactions, and the efficiency of mixing processes. The fact that these chemical signatures persist despite the diffuse and transient nature of bridges underscores the robustness of chemical traces in astrophysics. Ultimately, the study of chemical fingerprints in bridge gas reveals that these structures are not chemically anonymous. They carry detailed records of their origins and evolution, allowing astronomers to reconstruct interaction histories long after visual features fade. By preserving chemical memory, gas bridges provide a unique window into the baryonic life cycle of galaxies, linking past star formation to present-day intergalactic structures and future galactic evolution. Gas bridges do not form or evolve in isolation. Their properties depend strongly on the larger environment in which galaxy interactions occur. A bridge forming between two galaxies in relative isolation differs fundamentally from one forming within a galaxy group or a massive cluster. Group and cluster environments introduce additional gravitational actors, dense gaseous media, and higher relative velocities, all of which reshape how bridges form, how long they survive, and whether they remain detectable at all. In isolated galaxy pairs, the interaction can often be approximated as a two-body problem. The dominant forces are the mutual gravitational attraction of the two galaxies and the response of their gas and stellar components. Tidal forces act in a relatively clean way, stretching gas along the interaction axis and allowing a bridge to form between the galaxy's extended halos. The surrounding medium is usually tenuous, so once the bridge forms, its evolution is governed primarily by tidal geometry and internal gas physics. In these conditions, bridges can persist for several 100 million years and retain substantial neutral hydrogen fractions. Group environments are qualitatively different. A galaxy group contains multiple galaxies embedded within a common dark matter halo and immersed in an intra-group medium of diffuse hot gas. Interactions in groups are not strictly pairwise. Even when two galaxies are the primary participants in a close encounter, the gravitational field of the group as a whole influences their orbits. This additional gravitational complexity alters orbital paths, tidal strengths, and encounter velocities, leading to more varied and often less symmetric bridge morphologies. The intragroup medium introduces hydrodynamic effects, absent or weak in isolated pairs. Although less dense than the gas found in clusters, intragroup gas is still hot, typically at temperatures of millions of Kelvin. As galaxies and their stripped gas move through this medium, they experience ram pressure that compresses, heats, and strips gas from bridges. This interaction accelerates ionization and enhances gas loss, reducing the fraction of cold neutral material. As a result, bridges in groups tend to be more ionized and less massive in neutral hydrogen than those formed in isolation. Cluster environments amplify these effects dramatically. Galaxy clusters contain hundreds to thousands of galaxies embedded in deep gravitational potentials and filled with dense intracluster gas. This intracluster medium is extremely hot, often exceeding 10 million Kelvin, and its density is high enough to exert strong ram pressure on any gas moving through it. Relative velocities between galaxies and clusters are also much higher, commonly reaching hundreds to over 1,000 kilometers per second. These conditions fundamentally alter the fate of gas bridges. Enhanced stripping is one of the most important consequences of group and cluster environments. In clusters, ram pressure can exceed the gravitational restoring force of a galaxy's gas disk, stripping gas rapidly during a single passage through the cluster core. Gas bridges that begin to form through tidal interactions are quickly eroded by this pressure. Low-density regions are stripped first, leaving behind only the densest clumps or eliminating the bridge entirely. This stripping occurs on timescales much shorter than those associated with tidal evolution alone. Ionization is similarly enhanced. The hot intragroup or intracluster medium provides both thermal energy and a bath of high-energy photons that ionize stripped gas. Shock heating at the interface between cooler bridge gas and the hot medium raises temperatures and drives gas into highly ionized states. Once ionized, the gas becomes invisible in 21 centimeter emission, even if substantial mass remains present. Bridges in clusters therefore often fade observationally soon after formation, transitioning into diffuse, ionized structures detectable only through absorption or X-ray emission. These processes explain why long, continuous gas bridges are much rarer in clusters than in the field or in small groups. The combination of high relative velocities and strong ram pressure makes it difficult for gas to remain coherently connected over large distances. Even if tidal forces momentarily draw gas between galaxies, the hostile intracluster environment disrupts the structure before it can fully develop or persist. In contrast, stellar tidal features may survive longer, as stars are collisionless and unaffected by ram pressure, leading to situations where stellar bridges or tails exist without corresponding gas counterparts. Despite these challenges, gas bridges are observed in group environments, where conditions are intermediate. Several nearby galaxy groups exhibit extended high structures connecting multiple members. In these systems, bridges often link gas-rich galaxies with relatively low velocity dispersions, allowing tidal forces to dominate over ram pressure for extended periods. Observations reveal networks of diffuse gas-connecting group members, sometimes forming complex multi-branch structures rather than simple pairwise bridges. These group-scale bridges often show evidence of repeated interactions. Gas stripped during one encounter may be reshaped or reconnected during subsequent ones, producing extended gas distributions that trace the group's interaction history. Chemical signatures in such bridges frequently indicate mixed origins, reflecting contributions from multiple galaxies over time. This mixing is facilitated by the lower relative velocities and longer interaction times characteristic of groups compared to clusters. The presence of intragroup gas still influences survival. Bridges in groups tend to be more ionized and clumpier than those in isolation. Neutral hydrogen is often confined to denser regions, while more diffuse components are ionized and detectable only through absorption. The resulting structures are shorter-lived than isolated bridges, but significantly longer-lived than cluster counterparts, occupying an intermediate regime of persistence. Environmental dependence also affects where within groups bridges are found. they are more common in the outskirts of groups, where intragroup gas density and temperature are lower and relative velocities are modest. Near group centers, enhanced ram pressure and frequent interactions reduce survival times. This spatial dependence mirrors that seen in clusters, where gas-rich galaxies and residual gas structures are preferentially found at larger radii. Bridge survival is therefore a strong function of environment. In isolation, survival times can approach 1 billion years under favourable conditions. In groups, survival times are reduced to a few 100 million years, with increasing ionization and fragmentation over time. In clusters, coherent bridges may survive only briefly, if at all, before being stripped and ionized. This gradient reflects the increasing dominance of hydrodynamic over gravitational processes as environment density and velocity increase. The environmental influence extends beyond morphology and lifetime to the role bridges play in galaxy evolution. In isolated pairs, bridges can act as efficient channels for gas exchange, feeding star formation and altering gas budgets. In groups, bridges contribute to a shared gas reservoir, redistributing baryons among members and enriching the intragroup medium. In clusters, stripped bridge gas becomes part of the intracluster medium, contributing to its mass and metallicity, but no longer directly influencing individual galaxies through coherent accretion. Observed examples across environments highlight these trends. Isolated pairs often show clean, extended high bridges with clear velocity continuity. Groups display tangled multi-phase gas connections with partial ionization and chemical mixing. Clusters show truncated, ionized remnants or complete absence of detectable gas bridges, despite clear evidence of stellar interactions. Together, these observations demonstrate that gas bridges are not universal products of galaxy encounters, but environmentally regulated phenomena. The dependence on environment underscores the importance of considering large-scale context when interpreting gas bridges. A bridge's presence, composition, and longevity encode information not only about the interacting galaxies, but also about the density, temperature, and dynamics of the surrounding medium. Bridges therefore act as probes of environment as much as of interaction history. In summary, group and cluster environments fundamentally reshape gas bridges through enhanced stripping, heating, and ionization. Pair interactions in isolation favour long-lived, neutral bridges shaped primarily by tidal forces. Groups introduce additional gravitational complexity and moderate ram pressure, producing shorter-lived, partially ionized structures. Clusters impose extreme conditions that rapidly erase bridges, leaving behind diffuse ionized gas incorporated into the intracluster medium. This environmental dependence reveals gas bridges as sensitive indicators of how galaxies interact with both each other and their larger cosmic surroundings. Numerical simulations have become the primary theoretical tool for understanding gas bridges, allowing the complex interplay of gravity, hydrodynamics, heating, cooling, and feedback to be followed in a controlled, physically consistent way. Unlike analytic models, which must simplify geometry and physics, simulations can track the formation and evolution of bridges in full 3 dimensions, making quantitative predictions that can be compared directly with observations. At the same time, simulations reveal how much of the bridge population remains hidden from current instruments shaped by physical processes operating below present detection limits. Modern simulations of gas bridges are typically embedded within larger models of galaxy interactions or cosmological structure formation. 2 broad approaches are used. Idealized interaction simulations focus on a small number of galaxies placed on prescribed orbits, allowing detailed exploration of how orbital geometry, mass ratios, and gas content affect bridge formation. Cosmological simulations, by contrast, follow the evolution of large volumes of the universe, naturally producing galaxy interactions within their environmental context. Both approaches contribute complementary insights into bridge physics. Hydrodynamical techniques form the core of these simulations. Gas dynamics are treated using either particle-based methods or grid-based methods. In particle-based approaches, gas is represented by discrete elements that follow the flow and interact through smoothed hydrodynamic forces. In grid-based approaches, the simulation volume is divided into cells, and gas properties are evolved according to the equations of fluid dynamics. Each method has advantages and limitations. Particle-based methods handle large dynamic ranges in density well, while grid-based methods capture shocks and fluid instabilities more accurately. Hybrid methods attempt to combine these strengths. Regardless of the numerical scheme, simulations must incorporate a wide range of physical processes relevant to gas bridges. Gravity governs the orbital evolution of galaxies and the tidal forces that stretch gas into bridges. Radiative cooling allows gas to lose thermal energy, while heating from ultraviolet backgrounds, shocks, and feedback maintains ionization and temperature. Star formation and stellar feedback are often included to model gas consumption and energy injection, even though star formation in bridges is typically inefficient. The cumulative effect of these processes determines whether a bridge forms, how dense it becomes, and how long it survives. Resolution is a critical factor in shaping simulation predictions. Gas bridges are extended structures with low densities, meaning that their internal features can fall below the resolution limit of many simulations. Spatial resolution determines the smallest structures that can be resolved, while mass resolution sets the minimum gas mass that can be represented accurately. If resolution is insufficient, bridges may appear smoother, more diffuse, or less massive than they should be, or they may fail to form altogether. Resolution limits particularly affect predictions of cold gas fractions. In reality, gas bridges are multi-phase, containing neutral, warm, ionized, and sometimes molecular components. Capturing the formation of cold, dense clumps requires resolving small-scale cooling and compression. Many cosmological simulations lack the resolution to follow these processes explicitly, instead relying on subgrid models that approximate cooling and star formation. As a result, simulations often underpredict the amount of cold, neutral gas in bridges compared to observations of nearby systems. Despite these limitations, simulations show strong agreement with observed bridge morphologies on large scales. Simulated interactions naturally produce elongated gas structures connecting galaxies, with lengths, widths, and overall shapes comparable to those seen in radio observations. Velocity fields in simulations exhibit the same coherent gradients observed in real bridges, confirming that tidal forces and angular momentum redistribution can account for their kinematic properties. The alignment of simulated bridges with interaction axes and orbital planes matches observational trends, lending confidence to the underlying physical framework. Where discrepancies arise, they often point to unresolved physics rather than fundamental flaws. For example, simulations sometimes predict bridges that are more diffuse or more ionized than observed. This difference can arise from overly strong heating, insufficient cooling, or limited resolution that suppresses density enhancements. Conversely, some simulations produce dense, long-lived bridges in environments where observations suggest rapid dispersal, indicating that environmental effects such as ram pressure may be underestimated. Simulations consistently predict that only a fraction of bridge gas is detectable in neutral hydrogen emission. Large amounts of gas reside at column densities below current detection thresholds, or in ionized phases invisible to radio surveys. This prediction aligns with absorption line studies, which reveal extended ionized components associated with bridges. Simulations therefore suggest that observed bridges represent only the densest, most neutral portions of a much larger population of intergalactic gas connections. This leads to one of the most significant predictions from models. Many gas bridges remain undetected. In simulations, bridges form frequently during galaxy interactions. especially at earlier cosmic times when interactions were more common and gas fractions were higher. However, most simulated bridges are short-lived, low-density, and highly ionized. Their surface brightness falls below the sensitivity limits of current instruments, making them effectively invisible except through absorption against rare background sources. The predicted abundance of undetected bridges has important implications for baryon accounting. Simulations indicate that a non-negligible fraction of galactic gas passes through a bridge phase during its lifetime, temporarily residing outside galaxies while remaining dynamically connected. This transient reservoir contributes to the circumgalactic and intergalactic gas budgets and may account for some of the baryons missing from observational inventories. The bridge phase acts as an intermediate state between disk gas and diffuse halo or intergalactic gas. Predicted cold gas fractions within bridges vary widely depending on simulation parameters. In gas-rich, low-velocity interactions, simulations can produce bridges with substantial neutral fractions, consistent with observed nearby examples. In higher velocity or denser environments, predicted cold fractions drop sharply as heating and ionization dominate. This environmental dependence mirrors observational trends, reinforcing the idea that bridge properties are regulated by both interaction dynamics and surrounding medium. Simulations also explore the fate of bridge gas. Some gas falls back into one or both galaxies, contributing to future star formation. Some mixes into the circumgalactic medium, enriching halos with metals. Some is heated and dispersed into the intergalactic medium. The relative importance of these pathways depends on interaction geometry, mass ratios, and environment. By tracking individual gas elements, simulations provide a detailed accounting of how baryons circulate between galaxies and their surroundings. Future instruments are expected to test these predictions directly. Increased sensitivity and improved resolution at radio wavelengths will lower column density detection thresholds, revealing fainter and more extended neutral hydrogen structures. This will allow direct imaging of bridge components that are currently inferred only indirectly. At the same time, expanded ultraviolet and X-ray capabilities will probe ionized phases with greater sensitivity, mapping the full multi-phase structure of bridges. Simulations predict that future observations will reveal bridges that are longer, more diffuse, and more common than currently recognized. They also predict that many interactions produce overlapping networks of gas connections rather than simple pairwise bridges, especially in group environments. These structures may blur the distinction between individual bridges and the larger circumgalactic medium, reshaping observational classifications. The interplay between simulations and observations is iterative. Discrepancies motivate improvements in physical modelling, such as better treatments of cooling, feedback, and turbulence. Improved simulations guide observational strategies by identifying where and how bridges are most likely to be detected. Together, they refine understanding of gas bridges as dynamic, multi-phase structures integral to galaxy evolution. In summary, simulations predict that gas bridges are natural, frequent outcomes of galaxy interactions governed by well-understood physical processes. They reproduce observed morphologies and kinematics, while revealing a much larger hidden population shaped by resolution limits and detection thresholds. They highlight the importance of ionized and low-density gas components that escape current surveys, and predict that future instruments will uncover a richer and more complex network of intergalactic gas connections. Through simulations, gas bridges emerge not as rare anomalies, but as common, transient features in the life cycle of galactic gas. The long-term evolution of gas bridges is governed by a slow but inexorable progression from coherence to dispersal. Once formed, a bridge exists in a dynamically delicate state, sustained temporarily by the gravitational configuration of the interacting galaxies and by the inertia of the gas itself. Over time, however, a combination of ionization, heating, dynamical stretching, and environmental interaction erodes the structure. The fate of a gas bridge is therefore not to stabilize or mature, but to dissolve, redistribute its material, and vanish as a recognizable entity. The characteristic timescale for bridge evolution is set by orbital dynamics and gas physics rather than by internal gravity. In most environments, gas bridges persist for a few 100 million years. This timescale corresponds roughly to the period between close passages in a galaxy interaction or to the time required for the interacting galaxies to separate sufficiently that their overlapping gravitational influence weakens. During this interval, the bridge gradually elongates, thins, and loses density. Numerical models and observational constraints consistently place typical lifetimes in the range of a few 100 million years, with shorter lifetimes in dense environments and longer ones in relative isolation. Ionization plays a central role in this evolution. Even in the absence of strong local radiation sources, gas bridges are continuously exposed to the cosmic ultraviolet background. This diffuse radiation field permeates intergalactic space and is sufficient to ionize low-density hydrogen over long timescales. As the bridge expands and its density decreases, recombination rates fall rapidly, allowing ionization to dominate. Neutral hydrogen fractions decline steadily, and the gas transitions from a radio-detectable state to an ionized one. This transition does not imply the immediate loss of gas, but it does mark the observational disappearance of the bridge in neutral hydrogen surveys. Ionization is often accelerated by additional sources. Ultraviolet photons from the parent galaxies, especially from star-forming regions, contribute to maintaining ionization in nearby sections of the bridge. Shock heating from relative motion through halo gas further raises temperatures, pushing gas into ionized regimes where cooling is inefficient. Once ionized, the gas couples more strongly to surrounding hot media, enhancing mixing and dispersal. As coherence weakens, much of the bridge material is recycled into the circumgalactic halos of the interacting galaxies. This recycling occurs through a combination of gravitational fallback and hydrodynamic capture. Gas that remains within the potential wells of the halos can slow, cool slightly, and become part of the diffuse halo reservoir. This process enriches the circumgalactic medium with metals originally produced in galactic disks and redistributed through the bridge. Recycling is therefore an important pathway for the redistribution of baryons and heavy elements around galaxies. Accretion back onto galaxies represents another possible fate for a fraction of bridge gas. Under favourable conditions, gas flows along the bridge toward one galaxy, loses angular momentum through dissipation, and is incorporated into the outer disk or inner halo. This accretion is rarely rapid or efficient, but over hundreds of millions of years it can supply a meaningful amount of gas. The likelihood of accretion depends on the relative mass of the galaxies, the depth of their gravitational potentials, and the thermodynamic state of the gas. Cooler, denser gas is more readily accreted, while hot, ionized gas is more likely to remain in the halo or escape into the intergalactic medium. Not all bridge gas follows smooth pathways. Fragmentation can occur under certain conditions, producing clumps and filaments that evolve semi-independently. Fragmentation is driven by instabilities arising from turbulence, shear, and thermal contrasts between different gas phases. In some cases, denser clumps survive longer than the diffuse background, temporarily retaining identity even as the larger bridge dissolves. These fragments may eventually fall into a galaxy, disperse into the halo, or be shredded by further interactions. Fragmentation, however, does not lead to long-term stability. The clumps lack sufficient mass and dark matter support to become self-gravitating systems. In many cases, dissipation is smoother. Rather than breaking into discrete pieces, the bridge gradually fades as density decreases and ionization increases. The gas becomes part of a continuous, low-density medium that blends seamlessly into the surrounding circumgalactic or intergalactic gas. From an observational standpoint, this smooth dissipation is difficult to trace as it leaves no sharp boundaries or obvious remnants. the bridge simply ceases to be distinguishable as a structure, even though its material persists in redistributed form. The balance between fragmentation and smooth dissipation depends on initial conditions and environment. Bridges formed from relatively dense gas in low-velocity interactions are more prone to fragmentation, while those formed in hotter, more ionizing environments tend towards smooth dispersal. In all cases, the end state is similar: loss of coherence and assimilation into larger gas reservoirs. The rarity of permanent gas bridges follows directly from these physical constraints. Permanence would require sustained confinement, continuous replenishment, or self-gravity strong enough to resist dispersal. Gas bridges satisfy none of these conditions. They contain too little mass to bind themselves, lack dark matter halos to provide long-term gravitational support, and exist in environments that actively work against stability through heating and ionization. Even repeated interactions rarely reinforce the same bridge structure, as orbital configurations evolve and gas reservoirs are depleted or redistributed. Cosmic time further disfavors permanence. As galaxies evolve, their gas content declines, their halos heat, and interactions become less frequent or more destructive. The conditions that favour bridge formation were more common at earlier epochs, when galaxies were gas-rich and interactions were frequent. Even then, bridges remained transient. Over billions of years, successive cycles of formation and dispersal contribute to the gradual redistribution of baryons without leaving long-lived structures. From a broader perspective, the fate of gas bridges highlights the difference between dynamical connection and structural identity. Bridges connect galaxies temporarily, enabling exchange of gas and metals, but they do not become enduring features. Their role is functional rather than architectural. They act as pathways through which material moves, not as stable components of galactic systems. The disappearance of a bridge does not mark the end of its influence. Gas recycled into halos can later cool and accrete, influencing star formation long after the bridge itself has vanished. Gas dispersed into the intergalactic medium contributes to the diffuse baryon reservoir and alters the thermal and chemical state of the surrounding environment. In this way, the legacy of a bridge persists even as its form dissolves. Understanding the long-term evolution of gas bridges therefore requires shifting focus from structure to process. The bridge phase is a transient stage in the life cycle of galactic gas, linking periods of disk residence, halo circulation, and intergalactic dispersal. Its lifetime is short compared to the age of galaxies, but its impact on gas redistribution is significant. In summary, gas bridges evolve over hundreds of millions of years through a combination of ionization, heating, stretching, and mixing. They lose neutral gas through exposure to the cosmic ultraviolet background, recycle material into circumgalactic halos, and occasionally feed gas back into galaxies. Fragmentation may occur locally, but smooth dissipation is the dominant outcome. The absence of self-gravity and dark matter support ensures that bridges cannot become permanent structures. Their fate is to dissolve, leaving behind redistributed gas that continues to shape galaxy evolution in less visible but enduring ways. Gas bridges are best understood not as isolated curiosities, but as visible segments of a much larger and largely invisible gaseous infrastructure that permeates the universe. They appear briefly, glow faintly in specific wavelengths, and then dissolve, yet they trace pathways through which matter routinely moves between galaxies. In this sense, gas bridges act as temporary highlights within a continuous network of gas that connects galactic systems across a wide range of scales. On the largest scales, the universe is structured by the cosmic web, a vast arrangement of filaments, sheets, and nodes shaped by dark matter and traced by diffuse baryonic gas. These filaments funnel matter into galaxies and groups, regulating growth and star formation over billions of years. gas bridges operate on smaller scales but follow the same underlying principle. They arise where gravitational potentials overlap, where gas is displaced from one reservoir and drawn toward another. While cosmic filaments are primordial and long-lived, gas bridges are secondary and transient, yet both belong to the same hierarchy of connected gaseous structures. The relationship between gas bridges and cosmic filaments is therefore one of scale and origin rather than of kind. Cosmic filaments supply gas to galaxies from intergalactic space, while gas bridges redistribute gas already processed within galaxies. In many cases, bridges form within regions already embedded in larger filaments, effectively acting as substructures within the cosmic web. This nested architecture means that the flow of baryons is continuous across scales, from megaparsec-long filaments down to kiloparsec-scale bridges and finally into galactic disks. Within this framework, gas bridges play a critical role in redistributing baryons. They transfer gas between galaxies, move material from disks into halos, and contribute to the enrichment of the surrounding medium. Through bridges, metals produced by stars are transported far beyond their birthplaces, mixing into circumgalactic and intergalactic gas. This redistribution influences cooling rates, ionization states, and the future ability of gas to form stars elsewhere. Bridges therefore participate directly in the cosmic baryon cycle, acting as conduits rather than endpoints. This perspective challenges the traditional view of galaxies as closed or weakly interacting systems. Optical images give the impression of galaxies as isolated islands of stars separated by empty space. Gas bridges reveal a different reality. Galaxies continuously exchange matter with their surroundings and with each other. Gas flows out through feedback, is stripped during interactions, travels through bridges and halos, and may later return. The boundaries of a galaxy, when defined by gas rather than stars, are extended, porous, and dynamic. Seeing galaxies as open systems has profound implications for understanding their evolution. Star formation histories, chemical enrichment, and gas depletion cannot be fully explained by processes confined within stellar disks. External gas exchange, mediated by bridges and related structures, alters gas reservoirs and delays or prolongs star formation. A galaxy that appears quiescent in isolation may be sustained by intermittent inflows from interactions, while another may be quenched by losing gas through repeated stripping and bridge formation. Gas bridges also challenge the idea that galaxy evolution can be understood one system at a time. Bridges form only through interaction, and their effects extend beyond the two galaxies directly involved. Gas stripped into a bridge may later be captured by a third galaxy, mixed into a group halo, or dispersed into the intergalactic medium. In this way, interactions couple the evolutionary paths of multiple galaxies, especially in groups where encounters are frequent. Evolution becomes a collective process rather than an isolated one. This collective view is supported by chemical and kinematic evidence. Bridges carry the chemical signatures of their parent galaxies, and when mixing occurs, those signatures blend. Over time, repeated interactions can homogenize the chemical composition of gas within a group environment. Kinematically, bridges link the motions of galaxies, revealing shared dynamical histories. These connections demonstrate that galaxies co-evolve within common environments, influenced by the same reservoirs of gas and by each other's gravitational fields. Gas bridges also help explain discrepancies in baryon accounting. A significant fraction of baryonic matter predicted by cosmology is not found in stars or cold gas within galaxies. Bridges represent one of the pathways through which baryons spend time outside galaxies while remaining dynamically connected. Although individual bridges are short-lived, the bridge phase is common over cosmic time. Many baryons cycle through this phase, contributing to the diffuse gas detected in halos and the intergalactic medium. From this standpoint, the transient nature of bridges does not diminish their importance. Instead, it underscores their role as processes rather than structures. They are moments when the underlying gas network becomes temporarily visible. Once ionized or dispersed, the gas does not vanish. It simply rejoins the broader, less observable components of the network. Bridges are therefore snapshots of an ongoing circulation that operates continuously, even when it leaves no obvious morphological trace. The concept of cosmic infrastructure emphasizes that gas dynamics operate on interconnected scales. Dark matter sets the scaffolding, cosmic filaments supply material, halos store and recycle gas, and bridges redistribute it locally between galaxies. No single component dominates indefinitely. Instead, galaxy evolution emerges from the interaction of all these elements over time. Gas bridges are one of the clearest observational manifestations of this interconnectedness because they explicitly link distinct galactic systems. Understanding gas bridges in this broader context reshapes how interactions are interpreted. Rather than viewing bridges as byproducts or anomalies, they can be seen as integral features of the gas network that governs galaxy growth. Their presence signals active exchange, while their absence may indicate environments where gas has already been ionized, stripped, or redistributed beyond easy detection. This perspective also reframes the question of isolation. Truly isolated galaxies, entirely cut off from external gas exchange, may be rarer than once assumed. Even in low-density environments, past interactions may have left behind diffuse gas structures that continue to influence evolution. Over billions of years, the cumulative effect of these interactions and exchanges shapes the diversity of galaxies observed today. Gas bridges therefore reveal galaxy evolution as a collective, network-driven process. Galaxies grow, evolve, and transform not only through internal mechanisms, but through shared reservoirs of gas and repeated exchanges with neighbours. Bridges expose the channels through which this exchange occurs, briefly illuminating the infrastructure that normally remains hidden. In this sense, gas bridges are not peripheral features of the universe. They are expressions of its underlying connectivity. By studying them, it becomes clear that galaxies are nodes in a vast, dynamic system of matter flow, linked by structures that appear and disappear, but collectively govern how baryons move, mix, and evolve.